So yes, welcome to the 2023 HamSci Workshop, day number 2. I am Nathaniel Brazil, W2 NAF. And let's see where we're going today. There we go. So just as a reminder to everyone, I do apologize for this Zoom thing here for people who are in the room. I'm trying many different ways to get it to not be annoying for this person. Okay, so a reminder, the agenda for today is available online at hamsci.org/hamsci2023, and you can click the blue button for the agenda over here. We are on Zoom today from 12:30 UT, which is 8:30 a.m. Eastern Time now, until 16:30 UTC, which is 12:30 p.m. on Eastern Time. All of the oral sessions are going to be online. The poster sessions and the workshops this afternoon are going to be offline. But if you want to see the posters, you can go to the agenda, you can click on their titles, and most of the posters are posted there. Presentation files and recordings will be posted later this week. People have been asking about that. I'm getting the presenters to give me the final public version of all of their presentation files, and then I will post a link to that on the website. Same thing with the recordings. We'll post, I'm going to have Jason of Ham Radio 2.0 over here. He's going to be doing a very, very, very light editing of the raw files. He's basically going to get rid of the gaps between the long gaps at lunches and at the ends of the presentation. And he'll get that on YouTube as fast as possible. And then over the next few months, he'll work on editing down to the final archival version. Reminder for people both here and on Zoom, we have many amateur radio activities here at the HamSci Workshop. The Burgos Amateur Radio Club in Wilkes-Barre, the Scranton Pocono Amateur Radio Club here in Scranton, W3USR, they are all organizing a special event station, W3USR, which is located in room LSD 126. So if you are here at the workshop, you can be on the air and you can try and work people. If you are on Zoom or elsewhere, you can try and work us from wherever you are. Do we have any information what bands we're operating? We're on FT8 this morning on 40? 40. Okay, 40 meter FT8 right now. So we've got that going. We also have a VE session today, volunteer examiner session at 1:30 p.m. in room 125. So if you want to earn your amateur radio license, you can go over there and you can take your test. If you are new to amateur radio and you want to learn how to get your license, I recommend a couple of different things. One, you can visit Bob Anderson over at the ARRL booth. Wave your hand, Bob. So Bob, he'll come up in a minute from the American Radio Radio League in ARRL. It has a wonderful, absolutely wonderful educational books and tools to help you, not just help you pass your test, but really learn the amateur radio jargon, culture, the science behind it, all of that. So you have the ARRL here. I also have to recognize someone else who's here who also creates a license manual, and that's Dan Romanchik, KB6NU. Is Dan here? He should be at the ARGC table, and he has written the no-nonsense guides to getting your license. If you just want kind of the Cliff Notes version, you can go to him, and his website, you can get the technician version for free in PDF format. So he is here at the ARGC booth. So go meet Dan, and they will teach you all about how you get your amateur radio license. And if you want to see an exam session in progress, you can go over to LSD 125 and see what it looks like. We have this amateur radio through the ages exhibit on the second floor hallway. Here's a picture of my son Anthony looking at one of the display cases. So if you go on the HamSci website, if you're virtual, you can wait for his picture to show up at the banner, the rotating banner on the front. You can click it, and then it'll take you to a photo album so you can see the exhibit virtually. If you're here in person at 2:30 and at 4 p.m., you can meet over at the registration table, I believe. And Bill Gallagher, is Bill here? Bill's all the way in the back right there. He is the person who owns most of the radios in the exhibit, and he will give you a walking tour of the exhibit. At the same times, we have the soon-to-be-built new ARRL funded W3USR station. I'll be giving a tour of where that's going to go. We're going to meet over at the LSC 126 at the special event station, and then I'll take people upstairs to see that. There's also a number of parallel workshop sessions this afternoon. Please see your agenda for the room numbers. I think Ed here from the ARRL lab is going to give a couple of sessions. ARDC is going to give a session on how ARDC works. So if you have an idea for a project to be funded, they will answer all of your questions. Case Western has a number of presentations. We have a presentation from Wilkes University as well on teaching computer networking with the M17 project, which is a digital voice mode for amateur radio. So a lot of neat things happening here. So before we get on to our invited speakers, which is actually there's one other invited speaker. Get over to that in a minute. I would like to invite Bob Indervinson and Q1R to give us a few opening remarks from the American Radio Community.
Thanks, Nathaniel. Good morning. And welcome to this 2023 HamSci Workshop. I bring greetings from the worldwide community of radio amateurs that makes up ARRL, the National Association for Amateur Radio. I also want to give a shout out to many familiar faces that I've come to know through the Collegiate Amateur Radio program that ARRL organizes. We have monthly Zoom meetings that unite the colleges and college radio clubs around the United States. Stop by the booth if you'd like to talk to me a little bit about that program. ARRL was founded in 1914 on the premise of uniting hams to push the boundaries of their knowledge and skills to relay signals, first from state to state, later intercontinentally. And of course, today, when even our smallest, we say weakest signals reach globally and beyond. Throughout those years, ARRL has been amateur radio's witness and partner and advocate. No other organization works harder to promote and protect the citizens' right to discover radio in all of its forms and uses, and across all radio spectrum. In a world where radio, in all of its increasingly visible ways, and commercial demands treat frequencies as auction items, the collaborative work of our hams and scientists and students is more important than ever. Yes, to advance our understanding of radio, and so we can develop the next generation of hardware, software, and modes, but also to inspire the next generation of hams and scientists and technologists who will take up the pursuit of radio technology and radio communications. Our work demands an increasing attention on STEM outreach. Our work demands increasing the diversity of our ranks. And promoting radio to like-minded communities becomes another component of where do we find the next generation of hams. Friends, there's much work to do here, but today let's revel in the work that has brought us together, a community of friends whose signals know no boundaries and whose contributions to radio unite us in the common good. Thank you.
Thank you so much, Bob. I really appreciate it. All right. Thank you to the ARRL for having me here. Dr. Isaias Shun, you are here. So I'm also very happy to say that we have representation from NASA here. So I'd like to introduce Dr. Isaias Shun. He's a program scientist. Is that the right term, Isaias? Yeah, program scientist for NASA headquarters. And you specialize, one of the things you specialize in is citizen science, right?
Yeah, radio, radar.
And radio, radar, and many different things. So this is a very special year for NASA and citizen science in general. because we have, as you know, there are 2 eclipses coming up, and we are going on the rise of solar cycle 25. So I'd like to welcome Dr. Isaiah Shum to talk to us about this and NASA's Heliophysics Big Year. Welcome, Dr. Shum.
Okay, thank you, Nathaniel. Yeah, so as you can see in my title, it's 2 solar eclipses and solar max. We in NASA call it the heliophysics.
Isaiah,
Yeah.
make sure, why don't you stand right there so the people on Zoom can hear you?
Okay.
And you can point to things using
how
that,
to make it forward?
that way.
Okay, all right. So now we're there. Okay, so we also call it the heliophysics big year because the sun is doing some big things. Yeah, the sun is doing some big things, so that's why it's, and then it starts in October 2023 and heads to the solar max early 2025. So for that reason, we call it. So during this time, which is more than a year, a lot of things are happening, which the sun has to do. So that's why we call it heliophysics big year. So for those people who don't know what heliophysics is basically the sun and its effect on the geospace environment, the environment we live in, and the solar system and beyond. Beyond means as long as the effect of the sun, reaches. So we kind of have a working group and program office, basically to increase public engagement during this time where the sun is doing a lot of cool stuff, so that the public gets engaged. So NASA Heliophysics Division would like anticipating a huge amount of public participation. The public in this case, and this is the HamSci community basically. We want big participation and partnership engagement during the annular solar eclipse of October 14, 2023, total solar eclipse of April 8, 2023, and the solar max, which leads up to early January 2025. So you can see, all the programs about the big year and this NASA link. And I brought that image to just remind you how nice solar eclipse is. This is an image from the 2027 total solar eclipse across the United States, heading from the northwest to the southeast. So the second case, why does NASA care? Especially, why does NASA Heliophysics care? So it cares because that's, one of our strategic objectives is to study the sun and how does it interact with the Earth and the solar system, including space weather. For that reason, as much as you guys are interested, we are also interested. So we partner with groups and communities like the HamSci community, which work on this area. So this image shows, this nice image shows ultraviolet image captured by the NASA Solar Dynamic Observatory. And you see how dynamic the sun is. That means you see how how fast it changes. And at the same time, the effect will be seen in the entire geospace environment and the solar system. So this was actually shared by a lot of people across the world, the smiling sun, right? So, that's how dynamic the sun is. That's how the effect will also be dynamic. And to understand these changes, we have a NASA space weather program, which is called was established by an act called the ProSwift Act. Basically, what it does is we want to mature in science and technology so that we will be able to forecast space weather, which kind of empowers the ever-increasing technological society. And as we live in Earth and expanding into the universe, basically. So we need to understand the space weather and increase our forecasting capability. How does NASA does it? Basically, how does our division, my division, Heliophysics division does it? So this is how we do it. So these are called the Heliophysics fleet system. So you can see some of the spacecrafts here are already in operation, and some of them are in development. So by employing all this spacecrafts, we make critical measurements so that we understand the solar system, the effect of the sun, how does the properties, the dynamic nature of the sun, and we'll be able to understand its impact on the universe and on the geospace system. So next, so this is an official map of NASA for the upcoming solar eclipses. So you can download your own copy down, and there's a link if you like. And as you can see, the annular solar eclipse of October 14, 2023 is heading from southwest to northeast. And the total solar eclipse will be heading from I think the other way around. So this is the total solar eclipse track, and this one is the annular solar eclipse track. So so actually, it's just to give you a brief context and definition, and I think everybody knows that when the moon passes across the sun and between the sun and Earth, that's how we got a total an eclipse. So I think zooming in, so you see this image. So there is a lucky place. Yesterday we have heard from Dr. Riff that San Antonio, Texas is the lucky place to see both the annular and the total solar eclipse. So so there will be a lot of activities and also engagement in that area. I'm sure the Ham community is. I know you guys have been planning this for a long time with weekly weekly meetings. So I think you are on the right place. So you don't need advice from me. So this is just animation of a total solar eclipse. Basically, what this shows is when the moon is appearing between the sun and the earth, you see that two shadows. One is called the penumbra, the other is the umbra, and you see basically that's how an eclipse is created. This was from the program office, the big Heliophysics big office program office. I got this image from. So this is to kind of try to create a visualization. If any one of you want this video to share with public, we'll be happy to share with you so that how do you visualize it. So this is because solar eclipse is because of this three-body problem. Actually, all this has to be kind of aligned to create that rare, once in 50 years, perhaps. No, this time it was in 2027, right? We had it, but the next one will be far, right? So yeah, that was about solar eclipse. The next one is, we call it a big year because the sun is transitioning from a solar min to a solar max. So you can see Oh, actually, I switched. Yeah. So Solar Max, you can see in 2014 there will be Solar Max, and 2000, and this Solar Mean has to be in 2000. Let me see. Yeah, we are heading from Solar Mean to Solar Max in 2020, and then to 2025. So this is again an image from the ESAT probe to spacecraft telescope in extreme ultraviolet image of the sun. Captured this entire history of the sun over the sun over 2 solar cycles. So, and that is within our strategic objectives. That's why we're, encouraging to people get engaged in these activities. So a closer look onto the sun during Solar Max, and why we say it's a big year, because this is what's happening during Solar Max. You can see kind of a little dull sun, but during Solar Max, see how active the sun is. So it will be active in the solar system and in the environment. Its effect will be also active. So this image is again from the NASA Solar Dynamic Observatory, and the one, let me see, December, the Solar Max is December 29, Solar Mean images from December 2019, and Solar Max is April 2014. So that's why we call it, I'm just trying to show you why it's big deal. And then the other big program we do is citizen science. I'm a member of the citizen science working group, and during this Heliophysics big year, huge engagement with community of people is very much expected. So one way of participating, again, you guys are already doing this. A great way of participating if the amateur radio people to participate in large amount to collect as much data as possible, so that we'll be able to characterize, understand the ionosphere and the geospatial environment during eclipse time. Yeah, so because the HamSci group is a NASA citizen science project. So as you can see, Nathaniel and his colleagues cleverly, I congratulate Nathaniel for cleverly assembling this group of amateurs and professionals, so that the resources they have can be used for scientific investigation, funds for scientific discovery. So kind of applaud for Nathaniel. Yeah, it's not an easy thing, because there are people, amateur, who's having fun and hobby doing the radio, but there's the science. So bringing them to help in the science is something great, and within policy of the NASA Science Mission Directorate. Basically, there is a policy in the NASA Science Mission Directorate that to provide opportunities for US citizen science, encourage highly educated volunteers who can benefit NASA, through their experience. So community should not be just looking from outside and doing whatever NASA is doing. They have to be involved within NASA discoveries and that kind of thing. So leveraging existing community of citizen scientists for enthusiasm with a variety of projects, and connecting subject matter experts in NASA with citizen science community members. So whenever if a citizen science involved in ham radio is interested to engage with another scientist, there is an open door for them. That's what this policy is all about. So how do you do, at least in the heliophysics division, we have programs to accept to support citizen science projects. Already, Nathaniel has got some NASA-funded projects, but more and more in the future, we see a lot more collaboration, partnership with this community of people. Yeah, last but not least, I will bring your attention to the annual NASA Space App Challenge 2023, which is going to be in October 7 to 8, 2023. So let me give you a little bit start from what happened in 2022. Over 31,000 people were registered across 162 countries. So NASA subject matter expert put together a challenge using NASA open data and with 11 international partners across the globe. So there were last year, there were 20 challenges and 3,009 almost 3,100 project solutions were submitted, which is basically in those 2 days, October 1 and 2, the world came together basically. So that is our way of, using, science to bring the world community together. If you have feedback about, the 2022 Space App Challenge, I'll be happy to take them and provide to the organizers. I'm heavily involved in this activities. So I know among us that we have two people from Europe to share their work who solved a solution, who participated in solving in one of the NASA Space App Challenge last year. We'll later be hearing from their solution. I'm very familiar with their solution. Yeah. So with that, I'm happy to take questions.
Any questions? Any questions for this? Yes, Steve.
Yeah, Steve Walters. Could you just say what one or two of the challenges are that come out? Just curious, what are some examples, challenges?
Those are, those are embargoed until, because to be fair for, we don't open the challenges right now, closer to the challenge solution day. We are working on building the challenge right now.
I think a good way to answer your question might be 2 talks from now, we're going to have one of the global finalist teams who won last year's explaining their solution. So we'll hear from them.
Yeah, he asked about last year.
Oh, you're just asking in general.
Oh, okay. But the challenge are not open now, they are closed. So they will be open closer to November or October. Yeah.
Any other questions?
Okay.
Thank you so much for this. I really appreciate it. Thank you for your time. All right, we're going to move on to the invited speakers in a second. But I wanted to share something else first. So escape here. Close that out. So you know that there are many different people that make all of HamSci run. And one of the things we need is good graphics and branding. So I just want to recognize a few people here. So these recent graphics that you've seen, this HamSci Workshop 2023 banner, and this beautiful new HamSci Festivals of Eclipse Ionospheric Science. These were produced by our graphics designers here at the University of Scranton, Vicky Leho. And so I think she did a really nice job, so I just wanted to recognize her for that. I wanted to recognize one other graphics person. So many of you may be familiar with this image over here. And this is actually a photo of myself and my friend Poker Joe standing on the roof of my house in New Jersey a few years ago. And you can see that we are installing a little G5RV Junior up there. And so the person who took this photo is in this room. That's my mother, and we were all trying to present Casey. Thank you.
I can't find it on your website.
It's the, let's see, oops, it's there too. I have a rotating banner. So well, there's Anthony, so that's the one where you can click it and you can get to the amateur radio through the ages, and there, that one. Okay, yeah, and if you want this, I can send it to you too, so, yeah, I can probably make up a media kit page that has all that information on there. So, yes, so thank you, and thank you for letting me use the photo. Okay, next we are going to go on to our invited speakers. Let me load up the presentation here. Have that, and we'll go back to here for a second. So each year I try to bring in 2 invited tutorial speakers that get to give a little bit of a longer talk. It's not necessarily on the latest research, it's to help orient people to the different things that we're doing in the community. And I always try to bring in one person from the professional science community, and I try to bring in one person from the amateur radio to talk about the different perspectives. And of course, being that this is HamSci, often there's a fine line between the 2 communities, so it's a blurry line. People are members of both, but that's the goal behind here. So for this year's invited scientist tutorial, I'd like to welcome Dr. Joseph Cuba, who's going to talk to us about modeling the ionosphere with the SAMI 3. So Dr. Joseph Cuba completed his PhD in theoretical plasma physics at the University of Maryland in 1975. Following his graduation, he joined the Naval Research Laboratory as an NRC postdoc and eventually became a staff member. Between 1995 and 2018, he headed the Space Plasma Physics section, part of the Beam Physics branch at the Naval Research Laboratory. He is now a vice president of Syntec Technologies, whose clients include the US federal government. Dr. Cuba's main research interests include boundaries and wave phenomena in plasmas, physical processes governing the Earth's upper ionosphere, and approaches to modeling these systems. Over the last 2 decades, he has been dedicated to writing advanced computer codes to simulate these events, which incorporate algorithms capable of simulating their sheer complexity. Dr. Cuba is also, like Pat, a fellow of the American Geophysical Union, but then also a fellow of the American Physical Society. So does that make you like fellow squared? I also spoke with Joe this morning. He's planning on doing a SAMI 3 simulation of the upcoming 2 solar eclipses. So he is going to be able to give us an actual prediction of what he thinks the ionospheric electron densities will be for the next 2 eclipses. And we have plans to release that to the community ahead of time so that the whole community, the amateurs, can go ahead and download those electron densities and start using them. And my graduate student, Devin, doesn't know this yet, but he's going to be tasked with integrating that part in with this PyLab ray tracing program, and also try to get that delivered to the community, hopefully in time before this the October 2023 eclipse, so that people can actually run these ray traces on their own computers before the eclipse and do their own propagation predictions. So with that, I would like to welcome Dr. Joseph Cuba. She went read that, great. No, Control L. Okay, thank you.
Thank you, Nathaniel. before I start, a couple of things. One, again, thanks to inviting me to this conference. It's pretty interesting. Yesterday, Nathaniel mentioned that there are actually people in the audience that didn't know anything about ham science. I'm one of them. So yesterday I found rather fascinating, especially the enthusiasm of the community and the work that's going on. And I'll give Nathaniel a lot of credit for that, bringing all this together now. Second, last night, you know, he was kind enough to give me a nice plaque for the other speakers. And so I made a comment, I guess I have to give a good talk now. It's worse. This is literally true. Last night after the banquet, I went to my room and my oldest daughter called just to talk. And it turns out today was her birthday. So I said, what would you like for your birthday? And she said, Dad, just give a really, really good talk tomorrow. Now, this is the first birthday talk I've ever given, and I hope she enjoys it, even though she's not here. So with that, I'll start the presentation. Okay, so modeling the Earth's ionosphere with SAMI 3. I've worked with quite a few people, but the one I really want to acknowledge is the first one, Glenn Joyce. I spent a decade side by side working with him on building these models. Sadly, he passed away in 2011, so he hasn't been around for the last decade or so to enjoy some of the fruits of what we had done. For the presentation, okay, there it is. So what is the ionosphere? I think most of us know. I also talk a little bit about the plasmasphere. I'll spend about half of it about the ingredients of how you build such a model, what goes into it. I really won't talk about numerics, and then at the end, I'll spend half the time on some various results. So this is a depiction of the ionosphere actually to scale. As everyone I think knows, it's pretty much generated by the EUV from the sun. In this particular case, the sun is off on the left, so we have sunrise, it builds up. Kind of maximizes in the afternoon, and then at sunset, it dies away. And if we're lucky, every now and then we'll see these equatorial plasma bubbles that grow, and I'll talk about that later on. So a few things. It's I have 90 to 1,000 kilometers, maybe 90 to 1,000. It's a weakly collisional plasma in the sense the neutral density is quite a bit larger than the electron density for the most part. So collisions dominate the physics. It's a multi-ion plasma. It has a very low beta. Beta is a plasma parameter. It's the ratio of plasma pressure to magnetic field pressure. And when it's very small, like it is in the ionosphere, it means the magnetic field simply does not move. I mean, it's rigid. And you can treat things electrostatically. You don't have to worry about any of the dynamics associated with a magnetic field that's actually moving like they do in the magnetosphere. Jim LaBelle was talking about yesterday with the reconnection. It's a few thousand K, and then the conductivity along the magnetic field line is much greater than perpendicular. So you have a basic electric field that can map along the field line rather easily. This is just a schematic of a nominal profile of the ionospheric ions. In the E region, it's dominated by moleculars NO plus, O2 plus, and then in the ionosphere, it's largely O plus that we're familiar with. And then eventually there's a transition at some altitude to hydrogen, and it becomes a hydrogen dominated plasma at high altitude. This is just sort of a contour plot of the electron density as a function of latitude and altitude. This is normally what one would see in the daytime and after sunset, the so-called Appleton anomaly, where the dynamics is such as you can pick up plasma from an E cross B drift, and then it falls down under the force of gravity, and you get this bifurcation in the peaks of the maximum density. Out in the United States, we're somewhere out here, so this type of thing isn't really, quote, seen locally over the United States. Okay, so the ingredients of a model: photoionization, the neutral atmosphere, chemistry, the magnetic field, electric field, and dynamics. And by plasma dynamics, I mean solving plasma equations. For photoionization, we need to calculate how much is produced from photoionization. So it looks like a relatively simple formula, the first one. Second one, maybe not so much. But it gives a flavor for what we actually need when we build this thing. So on the far right, you see this phi of lambda, that's the solar flux. So that's the spectrum from the sun coming towards the earth as a function of wavelength. And we're interested in the EUV. So you have to know that. Then as the radiation propagates through the atmosphere, it actually gets absorbed. So it's sort of like in cartoonish, showing that the color is getting dimmer and dimmer as the atmosphere absorbs some of this energy. You finally come to some point where you're interested in knowing how many ions are produced, and you multiply it by a cross section, photoionization cross section. You sum up everything and then you multiply by the neutral density, and that gives you the production rate. So in the calculation now, we need to know what the solar flux is, and we need to know what the neutral density is, as well as cross sections. So for the solar flux, there are some empirical models developed, or relatively simple models. And the one I highlight here in red is called UVAC, developed by Phil Richards in the 90s. So for the most part, we use this generally in SAMI. And one of the reasons is it's just easy to use. It's only based on a couple of parameters that we know, and it works pretty well. A more sophisticated model is the FISM model developed by Phil Chamberlain at LASK. That's actually based on observations from the sun. They're using the Solar Dynamic Observatory over the last several years to actually capture what is the spectrum from the sun. And all that information is tabulated on their website, and you can download what the spectrum is for a given day that you're interested in. The neutral atmosphere, again, this is a plot of the neutrals as a function of altitude above 100 kilometers or so. Then each neutral then not decays, but falls off with a scale height that's proportional to 1 over its mass. So the heavy moleculars die off pretty quickly, so they fall away. And then the light ions, such as hydrogen or helium, have a much longer a scale height, so they can go to higher altitudes and persist longer. So how do we know what the neutral atmosphere is? Okay, again, in red is what we're using in SAMI 3. The top two are empirical models, ARRL Intro, that provides the density and temperature of the neutral atmosphere, and HWM14 provides the neutral winds. So these are models that one can download, and you just simply say, I'm interested in this latitude, this longitude, this altitude at this time, and it'll come back and tell you what the neutral atmosphere is. And this is all based on compiling satellite measurements over the last 20, 30, 40 years into a database that resembles basically climatology. On the other hand, there's also a number of first principle models where they solve the equations for the neutral atmosphere. And lately we've been working primarily with the TIE-GCM and the WACM-X models that were developed at NCAR, and also recently with Erich Becker's model, HIA MCM and NWRA that Nathaniel mentioned yesterday. Again, these WACM-X and the HIA MCM, I'll talk about results from them later on. These are models that go actually from the ground to about 400 to 500 kilometers, capturing, weather dynamics and the like. And the important aspect of these models that's missing in the empirical models is that these models have atmospheric waves and gravity waves. So we've heard a lot about gravity waves and perhaps triggering TIDs and the like. So these models capture that effect. So that's why it's important to use this type of a model rather than just simply an empirical model that doesn't have gravity waves. And then there's chemistry. I'm not a chemist, but you read books and they tell you about what's going on. So I'll just highlight the dominant ones. There's charge exchange. So in this case, you have hydrogen exchanges a electron with oxygen, and then you have a neutral hydrogen and a ionized oxygen. So this is a mechanism where you lose hydrogen and gain oxygen. And then there's a reverse reaction too here. So there's a whole list I'll show in a second of this type of a charge exchange with rates on how you lose ions and gain ions just based on chemistry. And then there's, of course, a recombination loss where, in this case, say O plus recombines with an electron and just eats it up. So it's just a loss mechanism. And so in our model, this is a table of what we have right now. I think other codes actually have more complicated chemistry, but this is sort of a basic set, minimal set, if you will. Magnetic field, again, Jim LaBelle showed a picture similar to this top one, the Earth being a bar magnet dipole with closed field lines and open field lines. So our original model development, we used something like this, but it's really not accurate. And there's a IGRF model, the International Geophysical Reference Field. We use the Richmond Apex version of this. And so in this bottom picture, the white line here is the magnetic equator. It deviates quite a bit from the geographic equator. And it has a really significant role in how the dynamics of the ionosphere behave on a global scale. One comment I'll make, as I say up here in this picture, we have open and closed field lines. In the SAMI 3 model, all of the field lines are closed, every single one. And so this top field line here actually goes out to Never Never Land and then comes back on the bottom. And the idea is there's no upper boundary condition to worry about. But then the other hand, when you get far out in space, there's nothing going on. So, you know, we eschew a boundary condition in favor of just having a large region where nothing happens. Okay, there's also electric fields in the ionosphere that dominate a lot of the transport, needless to say. In the low latitude ionosphere, the neutral wind generates a global electric field. In the low and mid latitude ionosphere, and this is electric field that makes this Appleton anomaly I showed earlier. So originally there was there is a Thayer-Scheeless model. It's an empirical model of this electric field, which we originally used. But then more recently, we now solve a potential equation. So you have an equation with the conductances, the drivers, and then you solve this numerically to determine what the electric field is. At high latitude, it's a little bit different because we have these currents coming in from the mesosphere and going out. And these are so-called region 1 and 2 current systems. And they generate a large convective electric field over the polar cap. So you get these plasma being dragged over the polar cap and circulating. So in our model right now, we primarily use Weimer. It's a empirical model. Again, it's based largely on solar wind conditions, and you get an answer. We also have worked with other groups and who self-consistently, again, solve an equation to determine what this electric field is from this current system. And I won't talk about that stuff today, but you know, we've worked with the Royce convection model and then with the remix model in Gamera at APL. Okay, and lastly, equations. I don't want to see everyone's eyes glaze over. And I'm not going to talk about these very much. I just want to make one point. So in this model, for the velocity equation, on the left-hand side, I think virtually every other group or model has 0. And that ignores this red term, which is ion inertia. And the reason they use 0 is for several reasons, but it's a good physical approximation for the ionosphere where new IN is big. So years ago, we took that path and we were having numerical issues. And one day Glenn came in and said, well, screw it. Let's just keep this term and solve it and make life easier for us. And it did. Made the code flexible, expandable relatively easily. The downside was time steps. A normal time step for a code when you had 0 might be many minutes. Now our time step is 2 seconds. So we do a lot more computational work, but computers are relatively free and fast now. So we chose that path. And it had an added advantage we actually didn't think about at the time is as you go into the plasmasphere, which is collisionless, if you have a 0 on the left-hand side here, the equations simply break down because they assume that nu IN is large and it's not anymore. By keeping this inertia along the magnetic field, then we can capture the physics in the collisionless plasmasphere pretty well. And velocities don't blow up or go insane. So we didn't appreciate that at the time. We did it for numerical reasons, but there was this added bonus we found. And the bottom equation here is the so-called potential equation I said that gets solved. And the point is what's driving it is the neutral wind dominating in the low mid latitude, and then the current systems at high latitude. And then we also have to include gravity when we study these equatorial plasma bubbles and the like. Numerics, I'll just say, because the magnetic field is so strong, we have 2 different types of motion in this system where along the magnetic field, the plasma can just free stream. Perpendicular, it can't free stream. It's kind of tied to the magnetic field. So its motion is basically an E cross B drift across this magnetic field. And so we take advantage of that numerically where the first equation here I have highlighted is along the magnetic field. And then we do a time step perpendicular. And both equations have different types of numerical solutions that are best fit for those equations. So we try to capture the best of both worlds by splitting in between parallel and perpendicular motion. I want to elaborate this, but we have a fixed non-orthogonal grid that looks like this. The lines here going from one hemisphere to the other are essentially magnetic field lines. And then internally, we have a grid to do the transport of the plasma, primarily with this, E cross B drift. So to summarize, in red are some highlights. We have the apex model, so we capture sort of a realistic magnetic field. There's a non-uniform or non-orthogonal grid that's relatively unique. All ions are equal. Because of this inclusion of this ion inertia term, everything's equal. The majority of other ionosphere models don't have all ions equal, i.e. they get treated separately. They might treat this O plus and H plus in the upper atmosphere with dynamics, and then the molecular is N2 plus, NO plus, and O2 plus are in the E region, and there's no transport, it's just photochemical. The other parts I've already said, so let's move on to some results. First, I'll talk about TIDs, then these equatorial plasma bubbles, and I'll talk about the impact of the Tonga eruption on the ionosphere thermosphere system. That didn't come up yesterday, so I don't know if you guys looked at the Tonga thing, but it did have an effect over North America. And then lastly, something relatively recent, so-called plasmasphere ducts and irregularities. So yesterday we heard a lot about TIDs and gravity waves, atmospheric waves, as well as geomagnetic forcing from the Aurora region. Another way to generate them is through large-scale seismic disturbances. And so here I've listed tsunamis, earthquakes, volcanoes, and UNEs, underground nuclear explosions. So a number of years ago, people were looking at this after the North Korean events occurred. And there were some papers actually in GRL about this, making measurements of the atmosphere and ionosphere and trying to triangulate where this event actually occurred. So today what I'm going to look into is not that, but tsunamis. So this is going too far. This is from NOAA, the 2011 Tohoku tsunami. I'm not sure what this actually depicts. It might be water height or something, but it's kind of a neat picture. And it shows the extent and range of the tsunami as it extends into the Pacific Ocean. And somewhere, I'm not sure where, but maybe around here is Hawaii. So it turns out at that time, John Makela, now at Illinois, had a camera at Mount Haleakala on Hawaii, and he was making observations of the 630 nanometer emissions. So these are emissions that when O+ recombines from an electron, you get some photons out, and he can actually capture them at night, even though it's very weak. And then these emissions primarily come from an altitude of 250 to 300 kilometers. So it's the lower part of the F region that they're monitoring. And so here's Hawaii here, and this is what he found. And lo and behold, you see all this brightening and darkening, and these are basically oscillations in the ionosphere generated by the tsunami. A sensitive mouse, so to speak. So if I stop it here, so the red line is actually where the tsunami is, but you can see ahead of the tsunami in the atmosphere, there are oscillations. So the idea is as the tsunami disturbs the ocean surface, it generates a wave that propagates into the atmosphere, into the ionosphere, and actually propagate faster than the tsunami's actually moving, and hence you get waves occurring ahead of the tsunami. So we did a simulation of this a number of years ago. Doug Drob at NRL came up with a formula, analytical formula for the blast wave associated with what you expect from a tsunami. And the idea basically here was analytically, we could determine what the perturbations on the neutral wind were as a function of time as this quote, tsunami wave passed over Hawaii. And so this is trying to illustrate what is the effect of this neutral perturbation in the winds on the ionosphere. And it comes in two primary ways. And it's shown in the equation here. The first way is this direct coupling with the neutrals, and this is along the magnetic field line. The second way is through the electric field, and in the potential equation to solve for the electric field, there's a parameter variable, the neutral wind. So if you change the neutral wind, you can change the electric field and so on. So in the top left panel is the perturbation in the neutral wind along the magnetic field. In the bottom left panel is the response of the ions along the magnetic field. So it's pretty much 1-to-1. You know, if the neutrals are going up, it just drags the ions with them. If the neutrals are going down the field, it drags the ions with them. And so the color contours on the left panels are essentially the same. What was interesting is the top right panel. Neutral wind perturbations perpendicular to the magnetic field can generate electric field. Because of the high conductivity along the magnetic field, this field maps from the source region all the way to the conjugate region. And then if one looks at, well, what are the perturbations associated with this perturbing neutral wind? In the lower right, they're the strongest actually where you're making the perturbation. This is where the winds are. But on the other hand, there's actually perturbations in the conjugate region some 40,000 kilometers away. So again, this has to do with the electric field coupling. And so we did two simulations. One simulation without the tsunami wave, and one with the tsunami wave, and then you subtract, and you can see what the effect of the tsunami wave is on the system. And on the left panel is the change in the TEC, vertical total electron content, column, number of electrons in a 1 meter square column from the ground up. And the numbers here are quite small. If you can read it, it's 0.1, plus or minus 0.1 tech units. Now, normally at, say, the night tech can be 5 or 10 units. So this is a really small fraction in perturbation, but this is how it goes. And so you can see it comes in from the top, and then we saw the conjugate region grow up, and now the wave has now gone through all the way to the southern hemisphere. And then on the right, this is the emission from the code. So, you know, this is over Hawaii, and this is the type of structure that was seen by John Makela and his group. But then we also see this conjugate effect. And so we go on, and then it just continues. So the novel thing in this particular simulation was this conjugate effect. So subsequently, John, he went and looked at various stations in the South Pacific to see, in fact, could you see this effect? And the answer was, because this is such a low level of perturbation, it's hard to detect it through the noise. So maybe he saw it, maybe he didn't. There was nothing conclusive to say. And this is just a graph of a comparison between what they saw in their emissions versus what we measured. The data is in black, the model's in red. At least for the first, 600 or so kilometers, we did a pretty good job on the phasing, although the amplitudes are a little bit off. So maybe our initial wave wasn't strong enough, but nonetheless, it captured the dominant features of what was observed. So that's just a summary. So the next topic is equatorial spread F. Again, I'll go to my friend John Makela. He made this image again at Mount Haleakala. Again, these 630 nanometer emissions. So I'll start and then talk. All right, so you see these large dark structures coming up that are structured. And these are these so-called equatorial plasma bubbles. I'll stop there. So the idea is in the equatorial region, the bottom side of the ionosphere can become unstable. And so it's a plasma of a low density at 250 kilometers actually gets sucked up into the top side through electrodynamic effects and an instability. And so you get these really low density regions at high altitude, and that's reflected in these dark regions in this image. And then the other thing that John did is he overlaid, you can see 3 curves, red, green, and blue, and they're the paths of GPS satellites. And then the symbols are actually where the satellites are at that particular time. And so aside from making these optical emission measurements, they also had a GPS receiver, and now they're receiving from these 3 satellites. And at this particular time, this blue satellite, the signal's passing through this disturbed region. And down on the lower right, they're making a measurement. And it turns out at this time, the blue line is when they're making a measurement, and then it goes empty, and then there's blue again. So they lost the signal when the signal from the GPS satellite passes through this disturbed region. Okay, so this is one of the big impacts of this equatorial spread F in the equatorial region is you have a really disturbed ionosphere. It can actually mess up GPS signals, and it does even more damage, I will say, to communications that operate at lower frequencies. So this has been an ongoing problem for a long time. So I'll show some results now using the Wacom X and the Haya MCM models. For Wacom X, the resolution, the grid scales are about 70 kilometers the high MCM, the grid scale is about 50 kilometers. So this is global. And it's probably the highest resolution runs to date. For SAMI 3, we use the same longitude grid as WACMX and high MCM, but our latitude grid is variable, where we have a very fine grid around the equator to pick up this neutral wind dynamo electric field to calculate that. And then at higher altitudes, it gets coarser. And then these codes are one-way coupled, and that WACMX and high MCM gives neutral information to SAMI 3, specifically the winds. But there's no feedback from SAMI 3 back to these models right now at the time in the versions I'm using. And a minor, well, maybe not a minor point, but we're also using a high order flux transport algorithm to reduce numerical fusion, which allows us to capture these bubbles with sharp gradients. So one of the issues regarding equatorial spread F is the so-called seed mechanism. You have an equilibrium. In order to get an instability to grow, you have to perturb the equilibrium. And then if it's unstable, thing blows up, so to speak. So there's always been talk about what in the atmosphere could be a seed or a trigger for spread F. And a lot of people would say it's gravity waves. And so in this slide, we've tried to show that that's the case. The top panel is the TEC based on the IMSIS and HWM models. And you can see everything is relatively smooth. Not much is happening, but in the bottom panel where we included gravity waves, you can see in the Atlantic sector these striations, and these are these these equatorial plasma bubbles rising up and breaking through in the low density region. Another difference, which was unexpected and needs more work, are these patches of high density at mid latitude. There have been observations of this, and I believe it's due to plasmasphere drainage. Plasma high up just sort of drains down and increases the density at lower altitudes. So coincidentally, if you will, it turns out the GOLD satellite mission was making observations of this type of effect over the Atlantic sector. So GOLD is an instrument on a geosynchronous satellite, focused over the Americas and the Atlantic sector and the Western Africa. And they take, again, images of emissions at, in this case, 135 nanometers or so. And the plot on the far right is from Richard Esley's paper, where actually you can see the Appleton anomaly, and then these structures going through. So this is like a global picture of these equatorial bubbles that have formed. And this is like a first. The middle panel is our simulation. Okay, so the data is for an October event of equinox. The simulation is for March, again, an equinox low. So we weren't trying to, quote, simulate this particular image. It was more fortuitous, but you can see on the same color scale, we get these striations through, similar to what they see here. So we're in fact, our model didn't give it, quote, as bright emissions as what was observed. So on the far left, I just changed the color scale where I reduced the Rayleighs from 40 to 12 just to highlight the structure. And looks, at first blush, pretty remarkably similar to what was observed. So this is, I think, a big plus for us. But you don't always see these bubbles forming. So in the top panel and bottom actually is a plot of the electron density as a function of longitude and altitude along the magnetic equator. And you can see some bubbles here and here. And these are for two different times. The top panel is for equinox at low F10.7. The bottom is a July run at high F10.7. So climatologically from studies, in the summertime, you don't see spread F. And so if I play this movie, you come along And here you can see, you know, in the March case, the thing just blows up. It goes completely unstable. On the other hand, on the bottom panel, we get some maybe rippling on the bottom of the ionosphere, but no bubbles or anything are forming. So this is generically consistent with, you know, observations. The actual details in physics, why this thing doesn't go unstable, we're still looking into. I don't have a great answer for that right now. Okay, so the next topic is the Tonga event, which occurred last January, a year ago. So with this event, we've worked with Sharon Vadas and Erich Becker at NWRA, and Erich did a higher MC run of this event based on some inputs from Sharon Vadas's Mesorock model. And we just published this recently. So a few things here on this particular graph or image. On the right is a contour plots of sort of the perturbed density. You have the density, I smooth it, I subtract the smooth density from the real density, and to give you some idea of the perturbations that's going on. And so at this particular time, you can see on the left, which is the vertical neutral wind from high MCM. And the color bar is not presented here. I guess it's hard to see. It's plus or minus 15 meters a second. And so there's nothing else going on because this is a really high vertical velocity. Normally vertical velocities in the neutral wind and the ionosphere or thermosphere is a few meters a second, not 15 meters a second. And then later on, as time went on, you know, this eruption generated a wave that propagated around the world, and then we generated these slices of bubbles. So then the animation, nothing, and boom, there goes Tonga. And then eventually in this region here, you have these long striations, and they're equatorial plasma bubbles generated by the event. And so this is another representation for the perturbation to the TEC. At this time, we actually had bubbles form, but then boom, there goes the event. And then we have bubbles forming in this region here. So again, after the fact, I'll just highlight this panel and this panel, this middle panel here with the yellow. These are measurements of the electron density, or ion density rather, by the IVM instrument on the ICON mission. Sadly, ICON died last fall, unbeknownst why, but anyway. So at this time, as you go through, this is several hours after the eruption. This is maybe 10, this is 12. You see these really large, strong bite outs in the density that developed and seemed to drift westward. And this panel down here is from the model results. So at this particular time, when they saw a lot of strong depletions, we didn't see anything. So it turns out our timing is off a bit from the model. Things were happening quicker than we found. But then later on, you see these large bubbles in the model, not necessarily at the same location as what was observed, but nonetheless, they were very large 2 to 3 order bite outs in the electron density. And subsequently, they persisted. We did not see this westward drift, what it looks like here. But the picture of actually these Tonga eruption generating these large scale bubbles was picked up in the model. Again, we're continuing to pursue this as time goes on. One other comparison to data, this is from Urcha Oz paper in Space Weather. This is an ionogram from Guam on the right. And the thing he pointed out here was after the daytime, you go into night, all of a sudden there was a strong post-sunset rise, sort of like a little break here. On the left is from the model, and we also see this large spike associated with the Tonga eruption that they see here. Again, the timing is off, but the qualitative features the same. And my last topic is the plasmasphere. This is the extension of the ionosphere into space on closed field lines. High density being greater than 10 to the 2, which isn't quote terribly high compared to ionospheric densities. A few thousand K, it's mostly hydrogen, but there is helium, and this image on the right is actually emissions from helium. This sharp cutoff or transition from green to black, that's the boundary of the plasmasphere. It's called the plasma pause. I indicated earlier it was collisionless, and then a schematic from a paper I found online is shown here. And this is sort of the canonical picture of a plasmasphere. It's basically a nice uniform donut that surrounds the Earth. But then the question arose, well, what about atmospheric waves? How do they affect the plasmasphere? And then the relevance to what we're doing here, I guess, because I saw yesterday someone was talking about VLF waves in the atmosphere. When you study VLF waves, there's a lot of talk between ducting and non-ducting of the waves. And the ducting is associated with columns of, say, enhanced or depleted density over a certain region that can trap the wave to go from one conjugate to the other conjugate, and then keep a relatively strong signal. So to that note, in terms of structure, years ago I got this email from my brother. It's 2015. Real or crap? So he found this, and click on the link, and it comes up with this. There are giant plasma tubes floating above the Earth. And so it's a really, really cool image, and it's a really cool caption. And so this is the kind of thing that is in the popular press, and I think it's kind of neat. Anyway, this came out of some work done at the radio interferomic system down in Australia, and a student actually did this work. So with interferometry, they could make measurements of various motions of the ionosphere at a fine scale, and then based on these observations, they made this reconstruction of what the inner magnetosphere / plasmasphere could look like vis-a-vis these quote giant tubes. And so this would be the type of a structure that could, say, duct VLF waves. So then the question is, can we reproduce something like that? So this again, that was from the one I had shown earlier for SAMI3 and WACM-X for equatorial plasma bubble development. The top panel is a isosurface of a density of 5 × 10⁻⁵. This is about L = 2. So you're at an altitude about 1 RE above the Earth. The bottom panel is for 10⁻�3. This is about L = 4. On the left is the SAMI3 WACM-X simulation that includes fluctuating mouse. You can see structure associated with the waves. The surfaces on the right are from this empirical model, HWM and IMSIS, and it's very smooth. On the top, you're relatively close to the Earth, and so the variations are sort of the diurnal variations of the sun going around the Earth. On the bottom, it's pretty uniform, like all the time. And so on the bottom right is just this canonical picture of the plasmasphere of a large donut with no structure. At a meeting a few weeks ago, I showed this, and one of my friends, Mears Oppenheim, said, well, apparently the plasmasphere is actually not like a donut, it's more like a pumpkin. So I thought that was a pretty good analogy. I quite didn't see it, but it's there. So as far as ducting is concerned, the calculation that was done is to make a TEC, but along the flux tube. So the normal total electron content that one can download is a vertical TEC, just straight up. So what I did here rather is calculate the TEC actually along the magnetic field line. And then it gets, well, DS is the coordinate along B. And then the B naught over B factor gives the fact that the flux tube increases in size as you go to higher altitude. So what this is going to show is a detrended DEC ducting. The top panel again is this empirical driven model. The bottom is quote Wacom X. And so it's latitude versus altitude, and the longitude for this particular event is in the American sector, sort of on the east coast of America. And so if I play the image at the high latitude, this is just high latitude stuff going on. But the important stuff is kind of look into the middle region here. So in this mid-latitude region, it's pretty bland and green. There's nothing happening. But when we include these gravity waves, we get these enhancements and depletions in the total TEC along the field line. So these are the type of things that can lead, I would say, to ducting. Again, this is actually relatively new and still under investigation, but I did find one paper from 2008, and there was a VLF transmitter here, and then they made observations of the VLF waves on the Demeter satellite and on the CREST satellite. And then on the right is the intensity of the emissions they observed from this VLF transmitter. And then the point is, they say that in fact, in these regions here between 1.5 and 2.5, these are ducted transmissions. Elsewhere, they're not ducted. So it turns out then, if you look at this figure, between -60 and say -30, and then 40 to 50 or 60, that does kind of agree with where they're seeing these enhanced emissions. So those is kind of gratifying. Again, it's not proof or anything, but it indicates in a direction to go, that these ducts that people talk about are associated with atmospheric waves. Again, this is going on right now in terms of research. That's a summary. So then the final summary page, everything I talked about is a so-called SAMI tree model, which is a three-dimensional model. The original model was called SAMI-2. That was developed in the late 1990s by Glenn Joyce and myself. And we did that in about 18 months, and we open sourced it in 2000. And then subsequently, we worked on SAMI-3, and this quote, SAMI-3 ESF is a three-dimensional model, but we only model a small, narrow longitude section of the ionosphere. To focus in on really high resolution dynamics of bubbles and the like. So there's been a lot more work done. Also looked at metal ion dynamics in the E layer, storm time dynamics, and now feel kind of a little remiss. I didn't read the program as clearly as I should have, because I saw there were a lot of talks yesterday about solar eclipses, with Nathaniel talked about. So we had done a number of papers on solar eclipses with SAMI-3. 2017, Doug Drob and I published a paper on basically a prediction. You know, the big Great American Eclipse is coming up. Here's our prediction of what we should see. And so after the fact, then you could compare our model prediction to reality. And so I thought the agreement was, quote, spectacular. But what do I mean by spectacular? Do I mean we agreed perfectly with it? No. What I mean was we were like 80% good and 20% off. And why that's spectacular is, so when you go to get more money for this research, you can say, I could do a really good job, but if you give me more money, I can even do a better job. So, I guess I shouldn't say that out loud to program managers in the audience, but be that as it may. So anyway, we were going to continue with this work on the eclipses that are coming up with Nathaniel, as he mentioned, and that should be pretty exciting. And then I actually have one more view graph. So there's a journal, Perspectives of Earth and Space Science, that's open access, and it's relatively new AGU publication. And there are a lot of articles from, quote, old timers with memoirs and historical perspectives of research in various fields in space and earth physics. So this was just published recently. And I alluded to it earlier in the last few graphs that we developed SAMI2 at NRL, Glenn Joyce and myself. And so this is actually a sort of a historical perspective and how the model was developed. It's not terribly technical. There are some equations, but they can be skipped. But nonetheless, it's, as I say, the backstory. It's like, I don't know, you see a product and you just think, oh, that's a great product, without thinking about how it actually came to be. And sometimes it came to be in some interesting, unexpected ways. So anyway, it's an article. As I said, it's open access, and anyone that would like to read it is welcome to read it, and I hope you enjoy it. Thank you.
Thank you so much for that. I really appreciate it. I think this work is so important for what we're doing, because with amateur radio, especially as we're trying to connect it to science, the scientists always want to know, well, how do you actually connect your RBN spots to the physics? And this is a really good way to do it. You have a physics-based model, we can now compare it with our observations, with our data, with our radio propagation, and now we can really link the physics, get to some of what's actually causing what we're seeing. And conversely, it's a good way to test these models and go for that spectacular result, right?
Yeah.
So, because then we can say, okay, we as amateurs, we are really making these actual observations. This is what's really happening. And the model doesn't quite match it. Why? Maybe the model needs to be adjusted. We might be able to give some feedback to help improve it and improve the understanding that way. So this is really great. Joe has been absolutely wonderful to work with. He's been very open and helpful, and so he has indicated that he will continue to be open and helpful. So I greatly appreciate it. So thank you. And you can tell your daughter that she got her. All right, I'm gonna move along. You can catch Joe on the coffee break because we need to move along with the program here to our next invited speaker. So, you want to get his talk out first, or are we going to read the bio first? I'll get the talk out and then I'll bring it back. So many of you know, but I'm sure some of you do not, that there is what I kind of consider our sister conference that happens approximately 6 months from now, and that's the ARRL Capper Digital Communications Conference. And that happens usually in the first or second week of September. And it is more of an engineering focused conference, also amateur radio, but more engineering focused and more science focused. And as you know, HamSci has a very close relationship with Capper. We're collaborating on the Personal Space Weather Station project. And I always try to bring all of my students over to the Capper conference. So when I was, the other thing you probably know is there's a lot of efforts nowadays to be more inclusive, bring in more diversity, recruit new young people, recruit people from all over. And so, we want to do that in amateur radio too, and in HamSci. And so, I've been thinking about, ways to do that, or I always keep my eye out for that. And when I went to, yes, I want to trust this.
You can trust me.
Yes, I know. I'm gonna trust. Yeah. So when I went to the last Capper Digital Communications Conference, I heard this man speak, and I said, "He's doing everything we need to do." And not only that, I found out there were actually neighboring towns. So he's from Montclair, New Jersey, and I'm from Bloomfield, New Jersey. So we go way back. That's right. And right. And then Bob Spoletic, he's from Belleville. So so we're all here. And Mary Lou's from Montclair. So so we all have these common roots. But anyway, so he is on an ARDC funded project at the National Radio Astronomy Observatory. All these acronyms are just going in my head. I'll just read what it says. Okay. Jesse Alexander, WB2IFS-3, is an amateur radio operator leading the project's efforts to introduce young people to the wonder of the electromagnetic spectrum through hands-on ham radio-based experiences. Jesse has been a licensed amateur radio operator since 1975 when he got hooked on amateur radio as a teenager, reading ARRL's QST magazines in the Montclair Public Library in New Jersey. The stories about hams communicating with each other from Antarctic science stations in small Caribbean islands, chatting in Morse code through satellites, bouncing signals off the moon, and providing life-saving support during natural disasters filled him with wonder and curiosity. Jesse has more than 30 years of experience in technical writing, designing for people and companies involved in IT, wireless communications, and telecommunications, and is an award-winning poet, trainer, and entrepreneur. Jesse holds a Bachelor of Science and Master's of Engineering degrees in Electrical Engineering from Howard University. He's a senior member of IEEE, Aries Races, ARRL OTC, OMIC ARTC, and FIST, and a life member of the Alpha Phi Alpha Fraternity Incorporated. And I'd also like to say that, so far he's been working on this project and he has been meeting with his students over Zoom, right? And only over Zoom. And we invited his students to come to this conference and for the first time meet their teacher in person. So we'd like to welcome his students that are over there. So let's give them a warm welcome. Let's give Jesse Alexander a warm welcome tonight.
All right. Thank you. I always have to start with thank you. Thank you to the Great Spirit for being here. Thank you to my ancestors. Thank you to Dr. Frizzell, and that was really fortuitous meeting another person from exit 148 on the Gordon State Parkway. Sounds like a Saturday Night Live joke. Anyway, so it was good, fortuitous in many ways, and a lot of things happened to bring us here. So I'm just going to go through this. I'm going to start off with an update of where we are. And I should say the students can feel free to introduce themselves. They said they wanted to be kind of cool. So all right, I respect that. So let's see. We're going to talk about the Supernova Learning Management System, where we are with that. We're going to talk about remembering, as in bringing together BIPOC and LGBTQ folks holding space in wireless and in STEM. We're going to talk about STEM identities, and we're going to talk about how we're designing the curriculum and that kind of thing, our partners, and then we'll give 7-3s and open for Q&A. All right, so this is the summary of the project. As we say, I used to do sales or software stuff. So as we say, I won't read the slide, then we proceed to read the slide. Okay, so, but I won't do that. So we are about midway into the program. We designed it for 10 students. We have 9, which is the number of change. The 9 students, we call our cohorts waves. And so the first wave, wave 1, consists of the 9 students, 3 of whom are here. There's stipends, and the idea is to leading to a technician's license. And the other objective is to create content for the Supernova LMS, which is based on Moodle. And I'm sure some of you who teach know what Moodle is. So the idea is after the after the 2-year period is done, that we will release to the wild the stuff that's in Supernova for anybody to use, colleges, universities, ham clubs, whoever. So that's what that's all about. And so that's where we are. This is our timeline. So we're beyond the design phase, and now we're at the point where we are bolting the wings on the plane as it's taxiing down the runway. We're about halfway through the Wave 1 pilot program. And we're getting ready to get the young folks ready for testing and going through the technician's license. And we've got lots of people to thank, and even in this early stage, there's so many people who have been involved, and I'm really looking forward to getting them through the testing process. We're planning for this summer. We just got the results of a survey that we did with the young folks, and we're going to figure out how to redesign the program so we can get them quickly to the general class upgrade for Wave 1. We're also preparing for the academic year in the fall of this year, and we're going to do the lessons learned from these groups, from this group of folks, and apply that to Wave 2, which will be 20 students the next time around. All right, so what's in it for you? You know, I used to do sales. What's in it for whom, right? So what's in it for the cohort or the wave is as follows. The big thing that I've added since I met with Nathaniel before is the idea of STEM identity, helping the young folks feel that not feel, but know that they are part of wireless technology. They are part of the science. This is part of who they are. And this is about reclaiming that, all right? We're also, the ham radio community gets new blood. We sound like vampires, don't we? New blood. Anyway, we get new blood and we get new ideas, and we get to see the hobby move in new directions. All right, and so that's what's going on there. And the NRAL also gets, ideally, a hiring pool of people who we can hire to do various things. And actually, the whole point to amateur radio is that you have a pool of people who have hands-on experience with wireless technologies. And if you want to know what that's like, here's an interesting test. And this is the test. This is actually the way I got this job, by the way. Go on LinkedIn and type in ham radio in the job search and see what comes up. Now, no employer, because there's no pecuniary interest, no employer can hire you as a ham radio operator, except maybe in education, there's exceptions, and also for emergency management. But you're going to see a lot of jobs for techs. You're going to see a lot of jobs for engineers, designers, people who are closely associated with antenna design, wireless systems design, that kind of stuff. So that is one of that's what's in it for the various communities of interest here. Moving on, I'm just going to do a little demo and see if this works. Okay, this is the Supernova program. This is the I'd
just like to give you a quick demonstration of the Supernova platform.
Oh, that's me.
Start off with from the perspective of a student and log in. This platform is based on the open source system Moodle, and it will be, once we get through, say in about 2 years' time, it will be available for anyone who wants to use it online. But we've got a few things that we have to deal with first to make it work well enough to do that. And we have to manage our content and figure out what's in and out and that kind of thing. So this basically shows you the dashboard that a prospective student or student would see. You can see which classes have been completed with the check marks, and you can see the classes that are ongoing. with the arrows and ones that have yet to be done. So I'm just going to go into the, some of these are classes and some of them are actual activities. Like in this case, there's a supernova survey that everyone had to complete that includes demographic information that we were collecting for reporting to the ARDC and others who are supporting us. It can also consist of lessons, and so here's a lesson. Example of lesson 1. You can have all kinds of media in the classes, everything from videos to audio and of course images and that kind of thing. The students are to click through assignments to see the full page and what activities they need to do and that kind of thing. So that's the way that works. And so this is just one of the lessons. This happens to be the first lesson. Now I'm going to go in as a teacher and quickly show you what it looks like from the teacher's perspective. So all the courses. So we'll go back to that first course. We can see who the participants are in that course. And I'll just pick on my friend Andy's student. And we can take a look at Andy's students, just about every kind of thing every kind of way Andy's student is interacting. We can see which classes, which courses in this case, Andy's student has taken. For our particular instance of Moodle, classes are basically what Moodle sees as courses. So we can see what courses our friend Andy's student took. We can also get reports about their activity. And I'm just going to click on the complete report and we can see whether or not they signed up for for appointments. There are, students can sign up for them. We can see how often they viewed some of the content. And we can see, and that's also here for some of the resources and that kind of thing. So we get up, and we also see whether or not they did the pre-class questionnaire. And all the responses that people had. So that's what it looks like. That's just a short demo of our platform. And thanks a lot for watching.
This is a song that was sung by enslaved people in these on, as some of my friends call it, Turtle Island, here in the United States of America. The song is a map. It talks about celestial bodies and which celestial bodies to follow if you want to become free. The song was sung to let people know when there was a good opportunity to escape to freedom. It also is a map. It talks about not only celestial bodies, but it also talks about rivers. It talks about 2 rivers, 2 hills, and it gives direction. This is an example of how, and I should say, if I were really to do this talk justice, I would start further back. I'd start in Africa. I would start in Turtle Island and other places where people looked at the sky, made decisions about how to plant, when to do things, when to actually make things happen. People have ownership and agency. BIPOC folks have ownership and agency in wireless technologies, in astronomy and astrophysics and that kind of thing. So what is going through here, what's happening here are some famous and not so famous people. We started off with the drum here. There are two drum circles here. And we're filling in people who have been involved in many cases at the beginning of wireless technologies. The person in the red shirt is a friend of mine that I met who's now Silent Key, KB3IIE, who was involved, who's one of the people I got involved with, excuse me. Let's go back. No. So I just wanted to talk a little bit about this. I apologize to the people on Zoom. I kind of got carried away and I forgot to use the microphone. So let me use the microphone and just say what's going on here quickly. These are pictures of people who were involved in wireless technologies in various forms, in various ways. We've got Navajo code talkers down in the lower left. We've got one of the first amateur radio operators, African-American descent. In the middle, we have Dr. West, Dr. Gladys West, who developed the technology behind GPS, satellite systems and the constellation and how it's supposed to work and interoperate. At the top right, we have one of the first African-American ham radio operators. That's a nice call. And below it is a person, Jesse Russell, who actually hired me from Howard University a long time ago. Jesse Russell was the manager of the Wireless Center of Excellence at AT&T Bell Labs a long time ago. And the interesting thing about him and others was that unbeknownst to me, I joined Bell Labs at a time where they actually described it as the quote Harlem Renaissance of Black technologists at Bell Labs. So I was here, if you go the heavily damped oscillation that is the hype curve. I was up here at the hype curve when I joined Bell Labs in 1982. They paid for my master's degree in electrical engineering at Howard. So Jesse Russell was the first supervisor I worked for. And interestingly enough, almost the last supervisor I worked for. He had been promoted multiple times. And actually I worked for him in a startup called Ink Networks for a little bit and that kind of thing. And the other thing I wanted to mention on mic is that the gentleman at the lower right-hand corner, KB3IIE, Ken, is a Silent Key now, but he was one of the people I met at Prince George's County when I first came there. And he was involved with ARRLs, RACES, Boy Scouts, Girl Scouts, Red Cross. It's hard. It's probably easier for me to list organizations he was not involved in. Okay, right? Because he was involved in a lot of stuff. So he was an inspiration and still is an inspiration. So I will dedicate part of this talk to him as the Silent Key. How many people have seen this? You've probably seen this before.
I'm having trouble hearing the audio.
Okay, should I?
No, you're fine. Just pause this for 1 second. Going to send.
Let's start it again.
You won't believe it, but you can talk to someone in space. Sam from Earth, calling space station. Can you hear me? This is Sam from Earth. Can you hear me?
If you want to talk to space, you need a really big antenna. Multi-elemented and made of aluminum.
Calling the space station. Can you hear me?
Oh, man. Did I do that? Wait a minute. Come back. I think I can. There it is. All right, let's go.
You won't believe it.
The good part.
This is Sam from Earth calling the space station.
Sam from Earth. 聞こえますか？聞こえますよ。
こんにちは。こちらは
ジャパニーズスペースステーションです。もしもし、連絡してくれてありがとう。聞こえますよ。
Okay, so this is a commercial. I found this commercial online. I shared it on LinkedIn. I never got so many hits on something I shared on LinkedIn. I mean, and I found it on Facebook. There are people, hams have been sharing this thing like gangbusters. I mean, isn't this ham radio? Isn't that how we do? You know, so anyway, let's move on. All right, so developing a STEM identity. There are three parts to developing a STEM identity, and I think we saw them demonstrated in the previous video. Competence, performance, and recognition. These are the things that you need to have a stake in whatever it is you're doing from a STEM standpoint. We're speaking specifically about ham radio, but I'm also looking forward and into the future for these young folks about what that future looks like. So these are the aspects of developing STEM identity, and all of these things are in ham radio. We share with each other. We help each other develop confidence. And competence. There's ability to see our performance. Like we take the exam, you know, and also all kinds of awards for proficiency and Morse code and that kind of thing. And then there are recognitions, awards, and other opportunities like that. So that's what this is about. Now I'm talking about some of the barriers to developing STEM identity, and specifically in ham radio. The number one thing is the cost right, of a lot of the equipment, but that's changing now with SDRs. A lot of the stuff that we do in the class actually involves using free stuff. Like web SDR is just so cool. I've been having so much fun with web SDR, and we got a lot of mileage out of that in the class. Lack of space, antennas, being in a remote location, access to mentorships, access to clubs, discrimination and fear of discrimination, the imposter syndrome. How does, and one of the things that happens is, especially with folks who, you know, are in the BIPOC community and my community, I mean, people are like, well, how does this lead to a job? Okay, it's real nice, you're doing that radio stuff, but, you know, how does that work? You know, and so here's some of the answers, and I hinted at the answer to how does this help me get a job? Right? Like if you want, and I said this to a friend, if you want proof, don't listen to me. I said, don't listen to me. Do a search on LinkedIn and see what shows up. Lots of stuff shows up. Interesting stuff shows up. So lack of support for family opposition in some cases, and that gets back to how does this lead to a job, right? Exposure to people in the ham community, and also being able to engage people from the ham community with your parents, with your family, so that they can say, okay, all right, I see where this is going. I think this is okay, you know. Just don't blow any fuses or burn it. Well, you can tell I'm dating myself. Just put a point in there. Anyway, really dating myself. Okay, anyway, political engagement. So I'm also talking about lack of infrastructure, right? I've been trying to engage, I'm a member, sort of a member of Engineers Without Borders. How many people are familiar with Engineers Without Borders? Okay, Engineers Without Borders, for, I'd probably say almost a year, and I keep saying, well, what about ham radio? What about radio? Why don't you use radio technology? And they're like, people need sanitation, you know, they need water, you know, that comes first, and then we can do the other stuff. They need power. How about that? Electricity, right? So that's an issue that has to be engaged outside of the ham community. I shouldn't say outside of, but we need to engage our political leaders in a discussion about making it so that infrastructure is available so that folks can play ham radio and be involved in ham radio. The other one is a big one, lack of free time. That's a big one. That's a tough one. Again, that's going to require political leadership and pressure on politicians. You know, I had a taste of it when I was in grad school. You know, I didn't have a car, so I had to take public transportation. You wait for hours for stuff, and then you're tired when you get there, and then, you know, who has the time, right? Just imagine never having a car or not having a car or access to a car and what that would look like for you. So those are issues that have to be dealt with as barriers to ham, to a ham identity, a developing one. The other concept I'm talking about is Ubuntu. I am because we are. Ubuntu is a concept, not just an operating system. It was a concept first, developed by, well, actually it's a South African concept that's very old, but Bishop Desmond Tutu promulgated it. And it basically, to make it brief, I am because we are. So here we have a bunch of identities, and then, well, it looks like a bunch of them are members of ARRL. So that is a group of people who support each other, work with each other, at least have the potential to do so, right? And then there's another group who are in OMIC, like me, who are members of OMIC, and they happen all to be members of ARRL. Again, people who support the three aspects of all of the people in this group of STEM identity. And then we press the wrong button, and then we press this button, and we see some people are members of Aries. Again, within the ARRL umbrella, so to speak. And so, and they're members of the Young Ladies Relay League. We had we had Rhea into RJ. Yeah, and she came and spoke to us about their organization, and it was a great talk. And I think one or two of the students, I don't know if any of the ones here present did it, but I think one or two students reached out to that organization to see if they can join, and they want licenses. So there's more pressure to get licenses, right? And then local clubs, okay, local DX societies and that kind of thing. All these are the circles or cloud. Yeah, I work in the cloud industry, my day job. All these are the circles or clouds in which we operate, where we get the reinforcement of our identities in STEM, and that's what this is all about. Right? So I'm going to talk a little bit about an incident that happened at DCC, which is kind of interesting. It sort of passed over a lot of people. When I first came in, someone asked me, "Are you in the right place?" And I made the joke that, well, yeah, I saw the antennas, stuff like that, so I figured I'm in the right place. And they're like, "Well, are you sure you're in the right place?" I'm like, "Yeah, you know, definitely. In fact, I'm giving a presentation in this place." And finally, someone came over to the person who's challenged me and said, "Look, that's Jesse Ellison, who's WP2I Fest. He's supposed to be here." So, you know, if I were a different person and whatnot, I might have left, you know, but I'd come too far, so I really wasn't going to leave. But this is a question I've had to deal with frequently in my Black male body, my Black male STEM identified body. I had to deal with this. Are you in the right place? Are you sure? I don't know. In a lot of ways, okay. So ham radio will have to change. It's changed because I've been in it. It's changed because of people like Ken, AB3IIE. It's changed by our presence and also by our activity. And that's what's in store for you all. I'm speaking to you three who were here. You're going to be changing this. And so that's where we're going on. That's where we're going. So we got to go beyond safe places. When I first did this, I was thinking about safe place. But no, we got to go beyond safe place. This is our place, right? This is where we belong. All right, so we're going to talk about this a little further. So I did a search at the beginning of this project for something that seems relatively simple. I wanted a BIPOC woman, a brown woman, a Black woman, holding a microphone in front of a radio. Could not find that to save my life. I even went to, what's that AI program? Crayon. I went to Crayon and typed it in, and Black woman holding microphone, ham radio, and the results are okay, except most people I know 10 fingers, and the microphone doesn't connect to their elbow and that kind of thing. So I gave up on that. I did get a great photo from KD2UCQ, Brenda Muhammad, who was involved with a mutual aid organization out in Long Island, or like we say in the area, Long Island. And that was the best that I could do. And of course, there's Uhuru, but she's fictional, right? So it was really hard to do this. And that's what has to change in ham radio. It should be an ordinary thing to see a Black woman holding a microphone and talking into a radio, like, duh, But anyway, moving right along, the Schlitz commercial, I just thought was hilarious. Some of this idea came from some of the people I work with, Lindell and Danielle. And it said, I think it was Lindell, said, isn't there a crazy commercial? Yeah, I said, there is. And the woman's bringing the beer. And yeah, I got that, I found it. So we're trying to move this thing, I mean, the technology this person has, is now about this size, right? Yeah, so we're getting there, right? So let's see. So let's move on. So one of the things about changing things is changing language. And so this is one of the things I was struggling with, and I'm probably going to end up asking you all's help on this when we're back together on Zoom to see if these actually make sense to you in light of the lessons. So I'm replacing Elmer with mentor, and I'm suggesting we use that word. Elmer is kind of gendered, so YL, young lady. I like new friend, old friend. Because the XYL is always problematic. If you're a married woman who happens to be a ham, how does that work, right? So, that kind of thing. An old man, I like old friend and or new friend if you're a new ham. So these are some suggestions about changing the language or looking at the way we refer to each other and talk to each other. Okay, this is a mind map of various sub-hobbies that actually I'm involved in, a lot of them. And so what I was going to challenge R9 is that part of STEM identity is finding your sub-hobby in here and seeing how you can make it fit. And you can switch sub-hobbies. You can go from one, you can have 2 or 3, or 4 or 5. But I was going to challenge folks to look at these sub-hobbies, and we are examining them as we go through the class. I got to play this because I just included the slide because I just think this video is so cool. So let's see if I'm going to play the whole thing. You get the idea. So these are just, this is really to you all. These are some of these sub hobbies, some of the income related hobbies you can be involved in. And I know we're under the tyranny of the clock, so I'll move through to the end. And we always end our classes with the new amateur code. And I will not read, I definitely won't read this one. And you can get this from our website and I'll be happy to send it to you. And this just goes into the curriculum design approach. And I touched on this before. Again, these are the old slides that were delivered at DCC, so I'm going to breeze through these because we're under the tyranny of the clock. I want to pause here just briefly and talk about the idea of minimal viable product. That is the technique we're using to develop content for Supernova. And the idea is that at every stage in the development, you've got something useful, right? And something that works. So that's essentially where we're going with the design. There, we also talked about STEM identity and cohort building. My colleague Danielle Rowland has been heavily involved in that, and that's really been helping the students. And we have a presence on Discord, which is quite useful as we're all coming to this conference and trying to figure out how to get around and stuff like that. And I don't have to tell Hams that you have to have a logistics channel, right? To get things done, right? And I just want to end with a thank you. I can't say thank you enough to our partners, our helpers, our friends, our givers of free material and all that kind of good stuff. Thank you, thank you, thank you. And these are folks that organizations we're looking to form partnerships with as we keep going. And always a help wanted. We're looking for speakers. We've got a few more steps to go in the grant. And so we're going to need some more speakers, more mentors, and more partnerships. This is how to contact me, and I'll just leave this up and say one final thank you to Dr. Fussell for having me and allowing me to speak. And I'm happy to answer any questions if we have time, but I feel like I've run down the clock. And I'm eating into a coffee break, which is dangerous. But I'll leave this up if you want to scan my contact information and contact me. So that's it. That's all I got.
I think we all appreciate it, right? Yeah. So we are well into our coffee break. So for this next session, I would like to introduce Matt Downs and Marcin I practiced this. Marcin Lezanowski. And I'll actually stop the screen share for a minute here so that we can see our guest speaker from Egypt. So if I double click him, say hi, Gamal.
Hi guys.
Say hello.
Hello.
Okay, great. There you
Can
go.
you hear me or?
Yes, we can hear you. You have to speak nice and loudly though.
Should I raise my voice?
And there's yes, that's good.
That's fine. That's better.
Yes, it's much better.
Okay.
And there's another member of the team on the call on hold. Can I make this bigger? Yes. So great. So I'm going to remove the pin over here. Yes. Dr. Harsha.
Hello, I'm Daniel. Yeah, how are you?
Nice to meet you.
Yeah, nice to meet you too. Yeah, it's great.
Where are you located?
Yeah, I'm in France now. Ah, okay, let's.
Your QTH France.
Hello.
Hello, I see you.
Yeah, hi.
Hey, Harsha.
Hi, Gamal. Yeah, okay, that's
Hi.
nice. Yeah, I'm good. Okay.
Thank you for joining us. Okay, so let me get this on the screen here. We'll get the screen share going. So I am pleased to announce the Friends of the Ionosphere, or FOTI, and they're going to be talking about the evaluation of global ionospheric electron density using simultaneous observations from amateur radio networks, including the International Space Station, the NeQuickG model for space weather prediction. So all of you heard in Isaias's talk earlier this morning about the NASA Space Apps Challenge that's coming up this October, right? So this team here, they were one of 35 global finalists from last year's Space Apps Challenge. So this project, known as the Fellowship of the Ionosphere, is a global finalist in the 2022 NASA Space Apps Challenge. The NASA Space Apps 2022 Challenge had over 31,400 registered participants from 162 countries and territories. And there were over 3,000 submissions from the over 5,300 teams. Global finalists, so this is a global finalist team, are ranked as one of the top 35 projects from all of these submissions. And so it's quite an effort to get all of them here, or at least some of them here, so Matt and Marcin. And we tried really, really, really hard to get Gamal here from Egypt as well. And unfortunately, he just couldn't get the visa in time. So we're encouraging him to try and get over to the US for the CDAR workshop this June. So we'll see if we can make that happen. So with that, I will turn it over to Marcin and Matt.
Thank you, Nathaniel. We'll talk today about our journey during and after the NASA Space Apps Hackathon in October last year. We and other teams had 48 hours to answer one of the 23 challenges suggested by the organizers. One of the challenges was calling all radio enthusiasts. It asked participants to develop an application that visualize electron density in the ionosphere using ham radio data and ISS measurements. Additional goal was to promote citizen scientists initiatives and sharing of data. On the challenge chat, that meant this fantastic people who were willing to spend one weekend building something interesting. Together, we created a multidisciplinary team with what was at the moment temporary name, the Fellowship of the Ionosphere. That's because we began our journey as strangers from distant lands. You already know Gamal, Matt, and me. We already had on a team Sila from Turkey, Harsha from India, and Daniel from the UK. After a long discussion, we set our goal, which was to develop a web application because it would allow it to be more accessible to people without the need of any technical knowledge. We also weren't sure about the direction that the project might take in the future, so we wanted it to be flexible for the upcoming changes. Also, we wanted to display multiple sources of data and possibly more than specified in the challenge, and be able to compare them against each other. Spoiler alert, due to the time constraints, we didn't manage to fully realize our goals in all aspects, but we would really love to share our preliminary findings and plans for the future. Our main goal today is to gather as much feedback as possible to steer the project into a direction that's most useful to the scientific community. Since our team was multidisciplinary, we wanted to be able to speed our work as much as possible. So we came up with this architecture to allow us to work in parallel. It's a React web app with fast API backend in Python and multiple data ingestion scripts in both Python and MATLAB. Same as before, it was our plan at the time, but the end result stayed pretty similar to what you see here. The three data sources we chose were ham radio reporting network, WHISPER, where good propagation might indicate high electron density in the ionosphere. Floating potential measurement unit on board the ISS, which measures the electron density directly, and NeQuickG, global ionospheric model. Each of these data sources are imperfect, but we realized they could potentially complement each other. Ham radio propagation can indicate ionospheric conditions up to the F layer. ISS measures the electron density only at specific altitude, location, and time, but above the maximum TEC of F layer. And the model can give us electron density at any location and time, but does not take the real world conditions into account. Therefore, it can be inaccurate. These three data sources also represent the three following parts of our presentation: ham, ISS, and model, and we'll end with short summary. With that said, I will hand over to Matt, who will talk about the ham and ISS parts.
Thank you, Martin, and hello. That's a big USL card. I've been on air as 2E1 GYP for 25 years, excuse me, this summer. Thinking back to the early days, my relationship, excuse me, with the propagation gods was not unlike that of a typical marriage. You know, one day it would be in a perfectly good mood and allow me to have a 5 and 9 QSO with a distant station, and the next it would just blank me with several dBs of noise for no apparent reason. But over the years, I've learned how to get along with this mysterious entity and, you know, pick up on its strange, quirky rules and behaviors. For example, I now know that if I jump in the car and switch on the radio and there's crappy French pop music where my favorite station should be, I know that Sporadic E is probably doing its thing. Likewise, I figured out when to call CQ on certain bands and when to not even bother. And this project was a great platform to dive into some of the science behind this. So the first part of our project was to use open source ham data to make observations about electron density in the ionosphere. So what do we mean by ham data? Well, it's just HF signal reports, really, the usual stuff, timestamps, bands, locations, power levels, that sort of thing. But the problem was that we needed this data en masse. And as much as I enjoy playing radio, sitting in my shack all day trying to make as many QSOs as possible just wouldn't have cut it for this. But luckily we have things like the WHISPER network, which I was going to talk about briefly, but seeing as every other presentation pretty much as mentioned, yeah, I'm going to assume everyone knows what it is. So we set up our own WHISPER station just to get an appreciation of how it worked. The slide, the image on the left there. Yes, I do have the smallest shack in the world. It's not just Harry Potter that lives in cupboards, closets, sorry. So yeah, and we just got active on that briefly, and the image on the right just shows us propagating out into Europe. So we knew that any spots that were long distance spots would likely be propagating via skywave. And so what we didn't realize, or what we didn't know at the time, was where this refraction was occurring. So we thought it'd be try and visualize that. So we wrote a Python script, which queried the WHISPER database for 2 hours of activity across all bands. And we used that data to derive two methods. The first method, it's fairly rudimentary. We simply took the station locations, separated all the bands into groups, and we tried to get rid of as many ground wave or line of sight propagation paths as we could by sort of ignoring everything under 100 kilometers. And then we derived the geographic midpoint of these links, or spots as they call them. And we fed that data to the dev team, and they produced a heat map. This heat map here is an early example of a 40-meter test that we did, where the red dots, or triangles as they are, represent stations, and the colours indicate station. So I beg your pardon, the amount of stations. So the density of midpoints, I beg your pardon. And so what we thought was, if these hotspots indicate midpoints, are they therefore a good indication of electron density? Kind of yes is the answer, but not entirely, because we also recognize that not all signals propagate via a single hop. You know, with multi-hops, caudal hopping, ducting, that kind of thing. And so whilst it might not account for that, we do feel that this is suggestive, at least, of electron density at those locations. Another thing you might know from the image is the lack of midpoints across, well, to be fair, like loads of it, but the North Atlantic being an obvious one. The reason for this is because the 40-meter, as you know, I'm sure the 40-meter band opens up at night as the D layer fades and the F layer comes into play. And conversely, it's not so great in the daytime, and that happens to be when we took this data set. The second method, we kind of went a bit weird with this. We did a bit experimental. When I look back, I think it was probably quite late in the hackathon when we did it. Same thing again, for what it's worth, I'll talk you through it. Python did all the heavy lifting with this. We binned off any ground wave or line of sight links as we did before. And then we assigned, for each spot, we assigned a arbitrary matrix value based on the transmit power minus the free space path loss, plus the received signal power, times 10% of the distance. And what we did after that is, for each path again, we identified where it crossed any others. And in the event that it crossed another path, we added the sum of the two paths together and tied that sum to that geographical point. So we ended up with a table of lat longs and values, which is just what you need to make a heat map. But we ran out of time on this one, unfortunately, so we couldn't see it through. But it is on our to-do list, because it'd be interesting to see what results it produce. Whilst we're on the subject of future work and to-do list, I'd just like to quickly share a couple of other things that we're looking at. One of them is multi-hops. Is it possible to identify skip zones and use that to visualize the hopping path of a signal? So the graph in the bottom of the screen there is whisper data, kindly provided by Ron K4RHG, who's allowed us to use his station as a bit of a guinea pig. Ron's QTH is very well placed because he has a high concentration of receive stations in a single point of azimuth from his station. And that's what that polar plot shows. That's not a antenna polar plot for those of you thinking that is one hell of a Yagi. It's actually a geographical polar plot. So in this case, it shows us that Ron's QTH, he has over 100 receive stations to the northeast of his location. And that's really good because it gives us a high resolution of spot data to play with. And when we take that spot data and we put it onto a graph, we kind of begin to see a pattern. But if we take that one step further and we use resources like QRZ.com, and we then consider station heights above sea level and antenna arrangement and things like that, then we can further define the graph. So for example, if we have a cluster of stations here in Scranton and they're receiving, let's say, a signal from Florida, and maybe one or two aren't, we might look at QRZ and realize that those one or two have antennas that are considerably off bearing from the transmit station. So when I say off bearing, not phase, because we expect the refraction to meddle with phase change anyway, as it does. off bearing. So the transmit antenna might be a horizontal dipole biased north-south, and the receive antennas might be horizontal dipoles biased east-west. And therefore, there's a fair bit of loss straight off the bat there. And we can manipulate the figures to start to see in the graph there. We don't know if we're looking at hops there, but we've really only just scratched the surface of this. But we're going to run with it and see where it goes. Oh, incidentally, I ran off a few polar plots for some of your stations. You might see your call sign up there. If you do operate Whisper and would like a polar plot, we can make that happen for you. Something else, the other thing we'd like to look at is propagation at VHF and UHF. Seems to be a bit unloved during this conference. And one of the ways you can do that is with data from weather balloons. You can count the refractive angle. Unfortunately for us, weather balloons data is really easy to get hold of with, I think it's 1,800 each day launched globally. You can download the data from the relevant weather service, or you can even live track and receive these things. Or if you want the complete experience, you can literally track, chase and recover them, as I've done once or twice when one's landed near to my house. You can see my son Joseph there with our latest recovery. Who needs video games and sports? You can spend your weekends taking shredded latex out of muddy fields. Anyway, bringing it back to the hackathon, ham data is great, but we wanted to make an app that was had as much depth as possible, and so we considered other data sources basically, and the ISS came to the rescue. The ISS, most of you are probably aware of the crossband repeater and digipeater and stuff, but it does have another party trick for us, which is its floating potential measurement unit. Yes, I'm reading that from the slide because I forget every time, or FPMU, which is a collection of 4 probes, which, amongst other things, measure the electron density and temperature of the local plasma environment, which is great for us because we get the topside electron density for free, really. And better still, NASA provides free public access to these to this data. So we downloaded this data, and what did we do with it? The image on the left shows FPMU data output. It shows electron density at varying heights in the F layer over a 24-hour period, which is cool. But it's the image on the right which is important, because that's the one we chose to use in our app. And what that shows us is the tracks, or the geographical tracks of the ISS, and the colours is electron density, with red being the higher and blue the contrast. And the thing I really like about this is that we know that electron density is higher, approximately plus or minus 20% over the equatorial region, and that's exactly what we see in this image. So this works really well in our app. I'm going to hand over to Gamal now, hopefully by the medium of Zoom, who can talk us through the third and final segment of the project. Gamal?
Yeah. Hey, mates.
Hey.
Hey.
It's all yours.
Thanks. Thanks, Dr. Nathaniel. Thanks, Marcel and Matt, the lovely audience that I was following yesterday. I wish if I were with you, standing here. We already have awesome data collected by ham radio and ISS, but there are still regions that lack data coverage. That's why modeling is proposed in our project for 2 reasons. The first one is to provide a complement coverage of data. The second reason is to be used as a cost function, an objective function, to be optimized later and to be enhanced using machine learning. That's why modeling is proposed, which is NeQuickG model. Matt, next slide, please. NeQuickG model is a global ionospheric model that provides better spatial and temporal resolution. And actually, it fits our timing constraints in our hackathon. That's why we use NeQuickG model. It was firstly developed by the International Center for Theoretical Physics, along with the University of Bruges. as a single frequency model to provide ionospheric corrections for the GNSS user community. Now, the European Space Agency officially approves the NeQuickG model as a signal of service for the Galileo users. And that's why we use this piece of code, which is an open access for code that fits, actually, that totally fits our hackathon requirements. From system point of view, NeQuickG model takes inputs. The first kind of inputs is the solar and geomagnetic indices. The second type of inputs that are used by our application, first, Bx, which is Galileo's coefficients. The second one are the timing coefficients, Tx. And the third one are the receiver coefficients. Then processing happens, and many outputs are being processed. One of them is the VTC or the electron density. Matt, next slide, please. As a requirement for our hackathon challenge, data use should be real-timed. Accordingly, we used Galileo's coefficients provided by NASA's Archive of Space Geodesy data. Matt, next slide, please. Here we downloaded a sample of these Galileo's coefficients, a text file that contains these values. Here we can get two very important pieces of information. The first one, you can see above this red grid, which is a date, which is 2019, month 7, day 11, then an hour based on GMT. So this value would be used as a Tx, or the timing constraints or timing coefficients used by our application. Though this red rectangle contains the Galileo's coefficients. Here we have A0 and A1 and A2 in the zoomed figure. Matt? So we already have the Tx as can be adjusted in the right slide. As you can see, we only adjust the month and the universal time. Then we already have the Galileo's coefficient from the NASA's Archive Geodesy data. So we just need to adjust our receiver position. So our application needs to have a two-dimensional grid of longitudes and latitudes. That's how we can get it through a resolution for the latitudes 2.5 and longitudes 5 respectively. So having Tx and Rx and Bx all is set. Matt, next slide, please. Just kind to show how parameters are going to be calculated. It's not calculated in a single shot of phase, but it's going to be calculated starting with setting the initial classes in Python code, setting the position and broadcasting and the timing coefficients, then computing the parameters, as you can see in the last void function in the middle. So initializing this function is going to trigger the first phase, which is stage 1 of parameters, then going to stage 2 and 3 and 4 and 5, cascaded stages in order to calculate these parameters, ending with many parameters. One of them is the VTC or the electron density. Matt, next slide, please. Here we go. We are now verifying that the output really works good. As you can see, that's the flipped vertical TST profile with heights. So for a certain latitude, which is 40, and longitude 100 degrees, for a certain date, which is month April, universal time 12, using our NeQuickG model, here we have the result. The curve is verified. Then we can move on to generate through the globe, not only at a certain latitude and certain longitude, then we are certain that we are getting good results. Matt, next slide, please. Here we go. Here is the CSV file that is going to be handed to the next phase, to my respectful colleagues, in order to generate this beautiful scene of colors. So we need to generate a CSV file that containing information at each grid in position. For example, latitude X and longitude Y, then you have an E dynasty. Having this huge CSV file with our required resolution, then we can have this CSV file to be delivered to the next stage. Matt, next slide, please. Okay, that's the first object to be fulfilled, is to provide a good coverage of data. The second one, when we have a model, then we are paving the way to have a cost function to be searched for, to be optimized later, to be even enhanced with different techniques. One of them is machine learning. So that was a research, that was a future research in our hackathon that worked before the deadline submission. So we were having a kind of optimization technique, the one which helped us so much, the particle swarm optimization. As you can see in the left, you have a kind of army of ants, and these ants are initially are randomly initialized in their positions, and they are updating their positions iteration by iteration until they reach this star, until they reach this optimized goal. So at the end of the day, we have X and Y that give you the optimum value of your objective function. In a nutshell, you can have a look at this flow chart of the PSO, particle swarm optimization algorithm, and we can notice that the particle swarm are updating their position cycle by cycle until they reach their optimum goal. So our target in this optimization is the reverse one. Here, we are going to have Galileo's coefficients at a certain time. So we have Bx and Tx. Then we are going to search for Rx. What are the positions through the globe that we can find the vertical electron density to be maximized for all range of heights? That was a task. Math. Voila. Here is the result. What does particle swarm optimization tells us? PSO tells us, yes, we have found our goal at about minus 8.8 and longitude 88 degrees Celsius, minus 88 degrees Celsius. Here we have it in this corner on the map. Sorry, I can show you because I'm video conferencing. So at this point, sorry, Matt, the one before, sorry, the slide before, Matt. Okay. Here, particle swarm tells you at certain position X and Y for a certain day at a certain time, you can find this spot on the globe that contains the highest electron density. Surprisingly, it surpasses in electron density for all the desired heights. In order to give a kind of check, we have checked so many points on the grid and a random one which is in blue, and we are going to check now that particle swarm optimization surpasses this blue curve in all heights. So PSO works fine. Matt. Yeah. Next slide, please. Here is our application that on the right. Here is thanks Martin for giving this very beautiful map, for this colored map. We can see the ham radio data, and here is the ISS. And finally, yes, come on, NeQuickG, come on. Where are you? Yes, here is NeQuickG model. You can see that as soon as we are increasing the resolution, we can have a kind of continuous map, which is very great. So we would be more than happy that you, the lovely audience, try to scan this QR code on the left to try our application. And I'm sure you will be happy with this. So take your time to scan it, and please, we will be very happy to have your feedback. Matt, next slide. At the end of the day, the project is in early progress, but we are still collaborating in weekly meetings to have it as a tangible project to be used by ham radios. And we invite people and our lovely audience to try the app, and please tell us your feedback. In the future, we would like to have it like a tool that is going to be used in research to understand the ionospheric electron density and its variations on hourly basis. So ham radio broadcast data from Whisper network is utilized to approximate the bottom side of the ionosphere. Meanwhile, the ISS provides measurements of the top side electron density. So NeQuickG model is going to give a study of electron density variations with great spatial and temporal resolution. But a very important note that some points on the globe are not realistic because that's a mathematical model that needs to be enhanced by huge data that we are going to tell again afterwards in research. At the end of the day, utilization of the 3 data sources could help in better ionospheric state prediction in the future. Matt, I think you hit me, Matt, right? Here are the links and resources. Feel free to contact us at space.fotsi@gmail.com, Fellowship of the Ionosphere, and feel free. Thanks, Matt. Okay. I think I took my time. I took much of time, right?
Thanks for now.
Thanks, Matt. Sorry, guys, for taking that long. Thank you. Guys, any questions?
That's good. Thank you so much. Any questions? They will be available all afternoon. Oh, you have a question from a site? The comment?
Yeah, go to give a little context what they have done. This was one of the hardest, actually the hardest challenge from last year, space time. So they managed to build the solution in 2 days, and they work remotely. So they need appreciation for what they have done, and for getting interested in this project. So I thank you very much, Mr.
Thank you.
Thank you very much for bringing. And thank you so much, Matt and Martine and Cosmo and Martin. Really appreciate it. And I'm going to turn it over to Dr. Christina Collins, who will moderate the rest of the session.
All right, thanks very much. So next up, we have Dr. Michael Hardinger at the Space Science Institute with his presentation, Listening to the Heliosphere, Making Space Data Audible for Citizen Science.
And Mike can go ahead and share a screen.
All right.
Great, will do. Can you hear me?
Yes, we can.
Sounds good. Oh, wait, hold on. I have to share audio. Yeah. Make sure I do that. Okay. Let me do this. And can you see my, hold on, sorry. So I can do this, swap. Okay, can you see my slides now? Looks good. Great, great. Yeah, thanks, Nathaniel, and thanks to all the organizers for letting me give this talk. And also want to thank my co-authors, especially Martin Archer and Emmanuel Masong, who provide a lot of material for this talk, and also NASA for support from the Citizen Science Seed Funding Program. So yeah, I'm going to be talking about using audio analysis to look at NASA satellite measurements and measurements in general, and how we can use audio for making unique discoveries that really complement visual analysis. And just to jump to the end, if you want to learn more about our project, feel free to go to our website. I'll be putting this link up several times throughout the talk. So I want to start with a question. Why don't heliophysics researchers use audio analysis? And I'll already preface this by saying I know that folks in the audience there use audio analysis all the time, and it's actually a rarity. If you look across the field of people who study the ionosphere, magnetosphere, near-Earth space environment, we practically never use audio analysis. We're always using visual analysis of things like time series and spectrograms that we'll use to design detection algorithms to look for different patterns in the data. And really, it's interesting because the real question is, why did we stop using audio analysis? As many of you know, a lot of the phenomena that we look at, particularly the plasma waves, they have names based on sounds that we heard when playing them through a speaker. Chorus, hiss, whistler waves. These are all names that we came up with after listening to these things through a speaker. And these are waves in the human audible range. I'm going to play one example from the Polar spacecraft, which people here are very, very familiar with because you can also hear these on the ground.
You may not realize.
Can you hear us, Mike? It's like a seance. Hello? I can type at him.
Sharing.
Lost audio?
Yep. Ironically, here you go.
Why did we lose audio?
Well, it was halfway through playing a sound sample.
You played a sound and his mic went away.
Okay,
And his mic went away. Somehow. Actually,
all right.
don't think it's on our side.
Can you all hear me now?
Yes, now we can hear you.
Now we can. All right. I was watching out in the lobby. All right.
Can you all hear me now?
Yes.
Okay. I had to go to an old school headset. I don't know why. Maybe my headset ran out of batteries. My apologies for that. It's unfortunate that happened in an audio focused talk. Let me share my screen again. And hopefully that doesn't happen again when I play audio. I don't know if that's going to be a common thing. But okay, let me jump back into that. Sorry for that. So yeah, big exception to this is ham radio operators. You all are using audio analysis all the time. And I just want to stress again, it's a real rarity because we don't usually use it in heliophysics research. So let me go to the next slide. So I'm going to be talking about using audio analysis to look at ultra low frequency waves. These are waves that are the lowest frequency plasma waves in the near Earth space environment. And they are having analogies with musical instruments. There's an analogy with sound waves. There's an analogy with waves on a string. And these are very much like musical instruments. There are waves that are kind of like in a wind instrument, the size of this cavity that the Earth's magnetic field carves out called the magnetosphere. The size of that cavity will basically tell you what kind of pitch you're going to hear. You know, a tuba will sound different than a piccolo. If it's bigger or smaller, you'll hear a different pitch. There's also like waves on a guitar string. The longer the string, the lower the pitch. There's waves like waves on a drum. So these are really below the human audible range. They're in the millihertz range, so time scales of a couple minutes. And so you can't hear them, but you can audify them by speeding up the playback. So why do we want to do this? Why do we want to use audio analysis? Well, there's lots of benefits to using the human auditory system. We're good at picking out certain patterns with the human auditory system. If people are interested, I can put some links in the chat later, but just Google the cocktail party problem and you'll get a ton of information about why the human auditory system is really unique in its pattern detection capabilities. And it's not an either or. We still want to use visual if we can, but having them both, bringing them both into play is really helpful. So this chart here tells you a little bit about how much you have to speed up the playback to hear ULF waves. This is basically the human audible range on the y-axis. This is frequency. And the human audible range is between these two dashed lines. It's about 20 hertz to 20 kilohertz. And if you want to hear a wave with a period of a couple minutes, you got to speed that up by about 10,000 to 100,000. So you get about a year of data going by in 6 minutes. Not good for looking at short events, but really good for looking at patterns like the types of waves you'll see during a geomagnetic storm over many days. And you get complex but repeatable patterns that we can't really see with our current algorithms. Hopefully the sound will play and won't make me mute again. Let me try. Okay, that was like a couple of days of data with the NOAA GOES satellite. And so that's basically, again, sped up by quite a bit. So over a couple of days, couple orbits, you were just hearing that in a couple seconds. So we wanted to explore data with this audio analysis, and a great opportunity to do that was led by Martin Archer over in the UK. He was working with schools in London, the London area, as part of really an education project, but what they did is they let the students explore data with audio and visual techniques using the open source Audacity software, which a lot of you are probably familiar with, and then also translating some of that information into an Excel spreadsheet to identify different types of patterns. This is not prescribed, but just turning them loose on the data, giving them a bit of information about space weather, space physics, they were able to pick out a recurring type of ULF wave activity that we thought was really rare, and they picked out 23 of these in 1 year. And we learned a lot more about that wave mode So much so that it was actually published in Space Weather with them as co-authors. So this is a really promising technique. And I'm just going to show you on the next slide a little bit more about that discovery. So that was basically about a week of NOAA GOES satellite data. And the students went through a year of this stuff and they picked out this pattern very frequently. What happens is this big pulse of energy from the solar wind, this coronal mass ejection, hits the magnetosphere, hits the Earth's magnetic field, and you get this blast of white noise. And then as the GOES satellite is flying through the same region of space every day, it sees these more discrete frequency waves, these smaller range of pitches. And the tone that they hear as they go through this day after day after day just keeps descending. And then that pattern is basically to do with how the magnetosphere, the magnetic environment, is retuning in response to that pulse from solar wind energy. The amount of plasma is changing, the magnetic field is changing, and you get this retuning of these guitar strings going down over time. So this is a really promising technique. We learned a lot about how UF waves evolve during storms because of that. And so we really wanted to turn this loose with a bigger data set, a bigger group of people working with, I shouldn't say a US audience, it's really an international audience. We wanted to take the tools that Martin was using and make them more user-friendly so you can do everything online with a single graphical user interface. And so we've been, with the support from NASA, we've been beta testing those tools over the last year with high school students and university students. And as of today, our GUI is ready, and I'm happy to report that and ask for your help. I'll be asking at the end of the talk for those who are interested. But our science question that we're going after with this project right now is understanding the magnetospheric harp. So this is basically, as you move away from the Earth, the magnetic field lines get longer. And generally, each of these, you can think of them like a string. As a satellite flies through them, you'll see a descending tone. As the field lines get longer, then as it comes back towards the Earth, you'll hear an ascending tone. And so that's what you see on this chart here. The frequency goes down on this yellow line, and then it comes back up. And so like, this is what the theories tells us, but we don't often see this actually. We usually see just a blip here, a blip there. Sometimes we just see white noise, and sometimes we see an ascending tone instead of a descending tone. So there's a lot we don't understand about what's going on, and we wanted to get help from citizen scientists to help us identify some of these waves and figure out when we see one situation or another situation. And we also want to use a lot more data. We're using more than 13 years of data from NASA's Themis mission with this new data set. So this is how you can help by going to this link. And again, I want to stress that ham radio operators are really the experts in audio analysis. You're using audio and visual all the time, and that's very rare. We don't do that at all. Practically no one else in the heliophysics field does that. So you can learn more about the project by going to that link, but I'm just going to play a video so you can see kind of what you will see if you sign up to do this project. You'll see the graphical user interface, which is basically here. You'll go through a tutorial like what's shown here. Let me skip ahead because I know time is short, but you can see the orbit plot on the left. There'll be some training. Oops. Sorry. Basically, you'll box events and you'll record some information. So again, the tutorial will walk you through what this looks like in the actual data. And I think this is actually an older version of this movie. There's another version of this movie where you can see the actual data. What you're seeing here is idealized data from a theory. So the way the tutorial works, it'll show you what the ideal case looks like. Then it'll show you what actual data looks like and what actual events will look like. And then it'll turn you loose and let you look at data that people haven't looked at before. So you won't get thrown to the wolves, so to speak. You'll have some training beforehand and you can see what it looks like. And let me just play real quick again what this sounds like in the ideal case. See if it'll play. So that's basically the descending tone, the ascending tone, and then you can have harmonics as well, just like you can have harmonics on a string. So let me go forward. Oh, this is what the real data looks like. And let me skip ahead because I know I'm short on time with that, but I can play that again if people are interested and show you the actual data. But I just want to close at the last slide here saying that so we definitely want the help of the ham community with this. Like I said, you all are the experts, but I also want to stress that it's not like the science that we're working on is disconnected from your science. These waves, these ultra low frequency waves, are closely connected with ionospheric impacts. They have a massive amount of energy. They put a massive amount of energy into the ionosphere. They affect the aurora. They affect ionospheric electron densities. This is basically this plot here shows you electron density in the ionosphere as a function of altitude at a single location. And over time, you see these amounts of electrons go up and down by a factor of 10 or more. And this is because of a wave that's happening in outer space. Similarly, if I play this movie of the aurora, you'll see that if you look at the time scale at the top, over time, there's this fading out of the aurora. You'll see it a little shortly. And then it'll come back over a time scale of maybe 5 or 6 or 7 minutes. So these things are common. There's all kinds of modulations in the aurora, the diffuse aurora, and different types of aurora. And there's different ways that these massive waves in outer space are basically dumping energy into the ionosphere and that you can see and detect. And so the question is, how do these waves affect radio wave propagation? Another question we heard from Jonathan Rizzo yesterday about VLF waves that you can detect with a ground-based receiver. And it turns out these much larger ULF waves, longer period waves, will modulate when you get these VLF waves. So you'll sometimes see in spacecraft data, VLF waves will come and go over a few minutes time scale. So it's another thing that would be very interesting to see if you can hear that with ground-based data sets. So there's lots of overlap with our science. And like I said, you all are experts on audio analysis. So if you're willing to help us, we'd greatly appreciate it. And just go to our website, click Get Involved, and help us look at data for the first time. And I think with that, I'll just close out. And again, thank you all for listening, and sorry for the technical difficulties there.
Nicely done. Thank you.
Thanks so much, Mike. We're a little short on time, but I think we can maybe make a time for 1 or 2 questions in the room. Anyone? All right.
There was one on chat too.
One on chat?
I'm reading it now. So the question is, positrons.
It's a comment.
Okay, yeah.
There are also positrons pinging between the poles from the Rorsat reactors. I was involved in this discovery back in the 80s.
That's awesome. That's really cool.
I also point out Michael Black is very tied in with the WhisperNet project, and I'm sorry, NPSK reporter. I know Phil Gladstone and Michael Black are on here, and they're helping us making sure the PSK reporter is all set to handle the solar eclipse things.
All right, thanks so much. And the URL again is listen.spacescience.org. So make sure to check that out. All right, then let's move on to Robert Wright, Whiskey 1 X-Ray Papa, with HamSci continuing a long tradition of amateur radio citizen science. Robert?
Thank you, Christina, for the nice introduction. If I know how to run this, just spacebar.
Spacebar or the therapies.
Okay, thank you. Thank you again, Christina. It's been a very, very, very good presentation, or today, or yesterday and today. And I feel a little bit out of place up here because I've spoken to amateur radio groups over the years, but I don't think I've ever been in such an astute organization as this. I kind of feel like the little kid crawling in under the tent of the circuit, under the flap of the circus tent. Anyway, good morning. I've got a little bit of a different presentation. This presentation is going to be a bit different from the preceding presentations, but I feel I have an important message that only the guys, it's not only for the guys with the beard, the gray beards like me, but with the younger generation, especially the younger generation. My message begins with a commendation that I received many years ago. That commendation I received in January of 1959, I believe. It's from the Air Research and Development Command, the National Academy of Science, and the American Radio Relay League, and it says, I just want to read this. Are pleased to acknowledge the outstanding services rendered by Robert Reif, that's me, operating amateur radio station K9AQP during the period of the United States program of the International Geophysical Year, January 1957, December 1958. Your unselfish cooperation with the ARRL IGY Propagation Research Project has contributed significantly to the world's scientific knowledge in the field of VHF ionospheric propagation, and it's signed by 3 gentlemen. Well, now that project was 66 years ago. There was something called the IGY. Now, what is that? The IGY stood for International Geophysical Union. This was the worldwide program of study of the Earth from July 1957 to December of 1958. The International well, I'm going to go through this quickly because I don't have a lot of time to go through all of this. You could put on a very good 1-hour presentation on the IGY and only touch the surface. But it was a minor thaw in the Cold War of the USSR that was taking place. So the first time since the end of World War II, the two were kind of talking to one another, or at least at the scientific level. All data was shared between all the participants. This was a big point because in a previous polar year study in the 1930s, some of the data didn't seem to get distributed the way it was supposed to. So the IGY, the dates were chosen to coincide with the peak of the current sunspot cycle, which was cycle 19, which was a record cycle if anybody goes back far enough. Both the US and the USSR proposed their satellites. Well, the Russians beat us to the punch when they launched Sputnik 1 in October of 1957. But we did kind of redeem ourselves when we launched Explorer 1 and had enough instruments on it to discover the Van Allen radiation belts. Now, the International Geophysical Year had 11 areas of study: Aurora, airflow, ergo, cosmic rays, geomagnetism, gravity, ionospheric physics, latitude and longitude, meteorology, oceanography, I can't read it either, please. I don't know how to get seismology and solar activity were the two others. Thank you, Mary. In addition,
You talk, I'll operate the computer.
Okay, that will work.
You stand right there.
Oh, okay,
There you go.
I'm fine.
There's a
Yeah,
microphone in there.
I see the owl size.
No, there's a microphone in there that you need to
Oh,
talk
okay.
into,
Oh,
so the
okay.
people on Zoom can hear you.
I thought this one was.
There's two microphones.
Okay, well, the launch, okay, go to the next slide, please. The American Radio Relay League started a program in cooperation with the Air Force to study PHF propagation on 50 and 2 meters primarily. And they were trying to study three primary things: trans-equatorial propagation, Aurora propagation, and sporadic E. Can I get to my okay, thank you. So the amateurs provided work, the amateurs provided work and had, well, something's. What we did is we made observations and sent them in every 2 weeks. And it was primarily just a signal report of an unusual propagation report. And it was headed up by just well, anyway, the propagation research project was a project to provide reports for that went to the American Radio Relay League, who collected them, sorted through them, organized them, and then submitted them to the Air Force Cambridge Research Lab for analysis. They encouraged amateurs to join the program. I joined the program in 1956. We had in 1957. I joined with a couple of other friends. I was a junior in high school, and it was very exciting. Now, about the only mode I operated at that time that fell into their category was Aurora on 2 meters. And Aurora being a difficult mode for some because it was CW only. So it was limited, but we had a great time. The sunspots numbers were so phenomenal. We had activity. I would run home from school, turn on the radio, raid the refrigerator for a bottle of Pepsi, and tune around, and on many occasions I would hear and it was great propagation. We typically could work the East Coast. New York, New Jersey was pretty easy. The New England states were a little more difficult. To the west, there wasn't a lot of activity, but I think the propagation would have worked. But Minnesota, Iowa, the North Dakota, South Dakota on really good days was fun. To the south was W4HHK, a famous call that people might recognize. W5RCI in Marks, Mississippi was a regular. W3GKP and W4AO, W2. Yeah, I was really, really consistent. We turned in these reports, got no feedback, unfortunately. But it was an exciting time, and I'm gonna go ahead now and then go back to my reading. I do this much better. The plan was to use the amateur radio operator to report observations of unusual context, i.e. DX. These reports were submitted to the ARRL twice a month. The ARRL had a special group to set up to gather the data for submission. It was a great time to be a ham radio operator. The high frequency bands were hot. It was also a good time to be on 6 or 2 meters. The MUF was getting over 50 meters. 50 megacycles was open on occasions. In the 1950s, there were not a lot of countries that were allowing 6-meter activity because 50 megahertz was channel 1 on TV. But there was enough activity in stations on worldwide to provide some exciting F2 context. I wasn't on 6 meters, but that was partly because we had channel 2, and channel 2 and 6 meters at the time were a bit of a problem with TVI when you were out of the fringe areas, like I was in northern Indiana. The high solar activity provided lots of aurora propagation above 6 and 2 meters. The 2-meter aurora was the mode I was most active in. Most of my reports to the PRP, the Propagation Research Project, were 2-meter aurora contacts. If you're not familiar with the mode, as I was saying, it sounds like turning noise on and off with a key. But you could get to propagate it, you could get to copy it pretty well. Because the cloud was moving and not irregular, there were many paths which caused this breakup of the CW node into mainly a noise component. It's kind of like the waves at the ocean. You got too far, or you just couldn't, you get back from the ocean, and instead of a crash, it sounds just like shh. Well, it's the same thing with Aurora. It just sounds like shh. AM was not usable at all. Sideband tends to work nowadays because you don't have a carrier, you supply your own carrier to help to modulate it, and that seems to help sideband work. The signals are generally good, strong, low power can provide very good contacts. As usual, a good antenna helps because the distortion of the AM is very poor copy. So CW was really the mode. During the IGY, I was only running 100 watts input. A tube called a 829B and a push-pull amplifier. The antenna was a 32-element collinear, the old bread spring, and it was up about 50 feet, but I made an awful lot of contacts. Everything in the ham shack at the time, except for a tunable shortwave radio, was home built. The converter for 2 meters, the power amplifier, the exciter was all homemade. Sometimes it took 2 or 3 times to get things to work in those days, but we made it. But my participation in the PRP ended in September of 1958 when I went off to college. But the activity of the PRP had convinced me that I wanted to study electrical engineering. I had HamSci to thank for helping me choose a career in which I spent the next 30 years of my life. I still consider myself an engineer. So what did I do for all those years? I only mention this because it is part of my point, which I will get to sooner or later. After college and 2 years in the Army, I came east to Massachusetts and started working for Sylvania Electronic Systems in Waltham, Massachusetts. One of the first projects I worked on was a phase lock tracking receiver that was used to receive signals from the moon. It was used to bring the TV signals back from the moon. Being an Apollo program was really exciting. I am one of the few remaining Apollo engineers. None of the people I worked with are survived except me. I mean, on a small project I was on. Is there anybody here who was an Apollo engineer or worked on the Apollo program? I think you did, yes. Dr. Wright, not me. But we're getting far and few between. Just with 60 years. Another project I worked on was a radio receiver that received radio signals on the on the bottom of the ocean by submarines. The project got me a ride on a nuclear submarine. We were sitting at the bottom of the Irish Sea, listening for the first test transmission from a high power transmitter in Wisconsin. The frequency was all of 72 and 80 hertz. But it worked, which was a good thing. I got paid. Then they brought me back from one of the last projects before I retired was a radio that was used on the space shuttle. And that was an exciting program. I really enjoyed that one. And it got me aboard the space shuttle. Unfortunately, it was sitting on the floor in the factory in California and not in orbit. But I've got to admit, there are a lot of other projects through the years, but most of them I can't talk about. And that's in some ways unfortunate. But the one project I am most proud of was the one I worked on while I was serving in the US Army. After basic training, I was assigned to White Sands Missile Range in New Mexico. There I was working with a civilian contractor as an electrical engineer wearing a green uniform. I was working with Bell Telephone Labs personnel. And the thing I was most proud about was the fact that we were working on an experimental radar that was designed to detect, track, and intercept the incoming ballistic missile. This was a forerunner of the system that the Ukrainians are using today to shoot down the Russian missiles and drones. So here comes the punchline. It was a citizens science radio amateur program that helped me choose a career in science and technology that led to a very rewarding and many times exciting career. The term science, citizen science, had not been coined yet. When I was in the PRP during the IGY 60+ years ago. But it was little different from the PSWS program that is now part of the citizen science program today. My message is simple. HamSci is only a new name. The value of the program is much larger than just the data they collect. To the young, I say, take part, join in the fun, excitement. Most of all, the reward and satisfaction of doing something your mother will be proud of. And to the older members, I say, keep up the good work of moving citizen science forward. There's no better task. Thank you very much. Any questions? Okay, thank you.
Thanks so much for that one. It's a great reminder of how much is still owed of the International Geophysical Year. And on the heels of Mike's talk, I was really impressed by how many of your stories were audio stories. All right, anybody on Zoom with questions? We can pass those along later because we're down to the last talk before lunch. We talked about what a challenge that can be. Okay, Vincent Ledvina is going to talk about the North Dakota Dual Aurora Camera version 2.0, a platform for citizen science and a use case for implementing best practices in open data and collaboration. Okay, great.
Sorry, it's a big file.
We've got it.
Lots of pictures.
People like pictures.
Yes. All right, well, thank you, Dr. Frizzell, for inviting me down to HamSci. I'm happy to be here. It only took me a few days to get here from Fairbanks, but we made it. Before I start, I just want to thank Dr. Tim Young, who's now the PI on this project. NODAC was founded almost 2 years ago, and it's gone through a bunch of development, and he's now the one leading it, and he's teaching right now, so I'm filling in for him, but just want to thank him for leading the project now, and then also all the other collaborators as well. So here's just a basic outline of my talk today. I'm going to be going over what NODAC is. So a lot of you may not know about the project, but I'm just going to give a brief overview and catch you all up to speed. And then I'll be going over the 2.0 version and what we've been doing recently. So why NODAC? Well, the motivation for NODAC really comes from the fact that Aurora cameras have benefits for the public and for scientists. So for the public, Aurora cameras are great tools for Aurora chasers and also for ham radio operators to see the Aurora and to use the Aurora for signal propagation and hearing the Aurora. So while you can infer the auroral activity based on satellite measurements, solar wind data and things like that, magnetometers, it's not a true analysis of what's going on. You really need to know what the sky is doing, what is a camera seeing, what is a person seeing on the ground. So that's what Aurora cameras can do. They can give you ground truth visualization of what the Aurora is actually doing. For scientists, Aurora cameras are used all the time in studies linking the different forms in the Aurora to what's going on in space. So cameras, and especially all sky imagers, are frequently used in studies to map the Aurora to outer space and figure out what's really causing it. And from a mid-latitude perspective, which is where NODAC is, it's in North Dakota, we get Aurora down in North Dakota actually pretty frequently, especially during geomagnetic storms. And during these storms, you get very unique auroral phenomena that often are not seen at high latitudes. And there's not a lot of Aurora cameras down at these mid-latitude regions. And when we were thinking about this project, the Martins Observatory, which is a facility owned and operated by UND, immediately came to mind as some place that we could host a camera. So all these sort of factors came together. We founded NODAC. And with that, also
it is a citizen science project, so it enables other Aurora chasers to go out there, take photos, and further contribute to other projects like Aurora Source, for example. Also, because I'll be explaining this later, it's all consumer off-the-shelf equipment. It's possible that this project could be expanded, beyond just one location, which we're already doing. But also somebody who's very enthusiastic could theoretically take these plans and build their own NODAC, for example. So now going into the specifics, we have two cameras. We have a north-facing video camera and an all-sky stills camera. So the north-facing video camera is a Sony A7S II paired with a Sony 24mm f1.4 GM lens, which gives it great light sensitivity. It's one of the best combinations you can get. And that's all consumer grade technology, and it's used for scientific purposes. I mean, this is high quality stuff. And the all-sky camera is actually just a very simple Canon Rebel T6 paired with a Sigma lens. And that setup, the all-sky setup actually just costs about $500. So it's really, really cheap. Powering everything is the IP time-lapse software. So we partnered with the Live Aurora network, and they let us use their IP time-lapse software, as well as they gave us two Pelco enclosures, which are just security camera enclosures that house both cameras and waterproof them. And what's great about this setup as well is that everything is power over Ethernet. So it's just one cable coming out of each enclosure, which minimizes the risk of water and moisture getting inside. So functionally, the north-facing video camera actually live streams Aurora to our YouTube channel, so you can check that out. I believe there's a power systems error right now, so the cameras are actually not going at the moment. But usually, this live stream is 24/7. It usually never goes down. And at night, the camera can sense Aurora. So it's always looking towards the northern horizon, and it's able to detect even really faint Aurora. The all-sky camera, on the other hand, just takes photos every 60 seconds. I believe it's a 30-second exposure. And then all these images are compiled into time lapses every single morning that are automatically posted to our Twitter account, Nodak_cameras. And as well as being on YouTube, it's also live streamed on the Live Aurora network site. That was part of the agreement. And what's really unique about this camera installation is that it is a partnership between the University of North Dakota, the Live Aurora network, and Aurora Source. So we're combining, all these different parties with different stakes in this project together to create a really cool citizen science project that has a lot of benefits. So here's just one data example. This is from April 10th, 2022 of a strong thermal emission velocity enhancement, otherwise known as STEVE. So we've been hearing a little bit about STEVE. We heard about it yesterday. This was actually sort of a phenomenon rediscovered by citizen scientists. It's always been around, but with the advancement of cameras in the modern day, photographers started to notice that there's this weird Aurora type light in the sky. So NODAC has seen a number of these events, and this is just one important one because apparently the STEVE actually formed from what's known as a SAR arc, a stable auroral red arc, which is a unique property of the STEVE. Is sometimes you can get formation from a SAR arc. So this is just kind of how the all sky images look and what you can expect from these data here. So one thing that we really want to do in the future, we haven't done this quite yet, is combine our imagery with citizen science imagery. So on the very bottom panel, this was from an older version of NODAC where we had a diagonal fisheye lens instead of a circular fisheye lens. So the view is a little bit different, but the idea is that you can use NODAC as one location, almost like one observer, and then combine photos from other observers in triangulation studies. So a very common way of determining the heights of Aurora and the spatial extent of certain auroral features is by using multiple perspectives and then using software to triangulate from these different locations the heights of these Aurora. And that's a very important property to understand. So these two images, the top row and the middle row, are actually images that I took from the exact same night I was out in North Dakota. And that white sort of purplish streak is a STEVE, but it's imaged from the side. So you can see that the perspective also changes quite a bit. And then the middle one is also my photography, and that's looking straight up. And you can see the picket fence formations there on the right, which is a hallmark thing of STEVE. So now that we've kind of gone over NODAC, this is sort of the timeline of the entire project. So January 2021 was really when NODAC went online, became operational. That's like the 1.0 version. And over the past 2 years, we've just been collecting data. We've been testing the cameras, making sure that we have everything down pat. We've also been presenting at different conferences and getting input and feedback about the project and how we can make it better. In June 2022, we actually did secure funding through NASA EPSCoR for a grant that would fund the project for the next year. So I was graduating at the time, so that was kind of a transitional period. I'm now at University of Alaska Fairbanks, and students are now heading up the project under the supervision of Dr. Tim Young. So with this NODAC 2.0, we've definitely taken the feedback we've gotten over the past 2 years and made some improvements. So first of all, with all the data that we have, now we're looking at using a citizen science platform to sift through the data and apply metadata to all these different images so that they can be easily searched for by the community, both the public and scientific communities, and that data can actually be useful. We're also looking to integrate that into a platform called Aurora X, which I'll be going over later. And then also, probably the most important aspect of this NODAC 2.0 rebrand, if you will, is our collaboration with the Nueda Hidatsa Sinish Tribal College on the Fort Berthold Reservation in North Dakota. We partnered with them and collaborated with them to not only provide an educational tool for them, since the Aurora really means a lot to their culture, but also, I'll be going over this later, but it provides another location where we can use that data to triangulate the Aurora, just using NODAC by itself. Also on the citizen science side of things, and also just the application of the project, we're still integrating it with Aurora Source, and also the Zooniverse project, which is the citizen science aspect I just mentioned. Then also we're looking for collaborations with other citizen science projects. So probably the most important aspect of this NODAC 2.0 is our collaboration. And we've always wanted NODAC to be more than just a camera, more than just a tool for Aurora chasers. We want this to be an educational tool. We want this to really impact people. So Dr. Tim Young has worked with the Nueda Hidatsa Sinish College on multiple projects before. So we approached them with this collaboration idea, and they were graciously willing to accept it. And we are now installing another NODAC camera out there about 250 miles west of Grand Forks, which is where the original NODAC camera is at. And that's going to provide not only a great resource for them, but also another camera for us to do triangulation studies, and also just more data that we can use in further analyses of Aurora. It also sort of provides a test bed for expanding NODAC to other locations. So this is going to be a great trial run for us to see whether or not the system can hold up in different environments. They're going to be installing it, I believe, at a more off-grid location than what we have. We have a nice observatory system, but they're going to be more off-grid. So we're going to see how NODAC performs there. Then also increasing the scientific utility. So right now, the data in NODAC, we're still going through everything, taking stake of sort of what we have, but we really want to improve the scientific utility of the data moving forward for this next 2.0 version. One step in that is improving the quality of the camera. So while the T6 does a pretty good job, as you've seen with the Steve example, you can get some nice imagery. What we really want is higher resolution so that we can more accurately see those picket fence formations in the Steve, for example, or just higher quality Aurora. So we're going to be upgrading to an A7R, which is a 33 megapixel camera compared with the 20 megapixel Canon T6. And then we're also going to be upgrading the north-facing camera to a Sony A7S III. So that's just the next iteration on the S2, which is what we have now. That's going to fix, if you notice in the live stream, if you've tuned in before, there's these pink fringes sort of at the bottoms of the image, and that's caused by just the sensor. And it's called amplification glow. So the A7S III fixes that and should help with identifying Aurora sort of at the boundaries of the image frame. Probably the most exciting thing is integrating our data into Aurora X. So Aurora X is a project run by the University of Calgary. It's a database of auroral all-sky imagery. It's mainly used for Themis, but it also has the capability of taking in other projects' data. So what we're going to be doing is partnering with them and using their platform to put in NODAC data, and that allows scientists then to use Aurora X to find satellite conjunctions. So that's very important for studying auroras. You want not only the optical imagery, but you also want a satellite flying over the aurora so you can get in situ data and then correlate that with what you're seeing on the ground. Also, making the data open source is a top priority. So we're going to be looking at publishing the data on sites like Zenodo. So that's a free open source site that gives the data a DOI, digital object identifier, which you've probably seen in papers, but it can also be used for data as well. And we'll be doing that soon once we've curated the data and cleaned it all up with all the metadata that I've been mentioning before. Some of these metadata will be generated with the Zooniverse project. So Zooniverse is an online platform where people can design their own citizen science projects, upload their data, and use citizen science to discover new things. So we're going to have citizen science project with two main goals. The first one is to identify Aurora in the different nights of images. So obviously we have all these nights of images from both cameras, but we don't know whether there's Aurora or not. So part of that is using citizen scientists to go in and say, hey, there's Aurora in that, let's flag it, and then assign a metadata tag to it so we can only upload, for example, those nights of Aurora into Aurora X. Also then from that curated data set, looking at the different types of Aurora will let us narrow down sort of like, let's say, for example, whether Steve was seen one night, what were the solar wind conditions at the time, what were the magnetometers doing, et cetera. So we're going to be launching that Zooniverse project later this year, and details will be posted on the appropriate platforms, HamSci, Google Group, all that fun stuff. And then Aurorasaurus was mentioned earlier today. It's a NASA citizen science project. And Aurorasaurus was an original collaborator of NODAC, but we're also using the platform to incorporate the cameras directly into the auroral oval map. So for those of you who are not familiar with Aurorasaurus, they crowdsource reports of Aurora from citizen scientists and then overlay that with the Ovation Prime prediction, which is a NOAA prediction. And that sort of gives you an estimate of where the Aurora is supposed to be seen versus where it's actually being seen. So our goal is to have little NODAC camera icons in both locations, and users can just click on those and see exactly what's going on. And there's also potential then to use, there's a function in IP time-lapse that can detect Aurora on the cameras. There's a possibility that we could use that as sort of an Aurora alert and a sort of feature type thing. So timeline for all this is kind of where things get interesting, is that we really want all this to be done by the end of the year. And we're making really good progress now that there's a whole team of students at UND working on the citizen science project and getting the code written for Aurora X. So there's sort of the list that, you know, the order that we want to do things. And what's really important for this group is, you know, we're going to be posting everything, making everything open source, and I'll be communicating all the details with you all on the Google group, HamSci, and also in the, you know, necessary listservs like CDAR and the GEM community newsletter and things like that. So just some conclusions and final remarks. This is the next iteration of NODAC, which is an agile citizen science project. And by agile, I don't mean we're quick on our feet, but we are quick to respond to community changes. We're a lean team, and we are very quick to pivot and adjust things as necessary. NODAC serves both the public and scientific audiences. So whether you're a ham trying to use the Aurora to propagate your signals, or you're a scientist looking to study Steves or other interesting Aurora, we have data that could be useful to you. And what's really cool is the platform can be expanded to other locations. And the fact that we use all consumer off-the-shelf equipment means that potentially you could have a NODAC in your backyard, who knows? And finally, we like to collaborate with other citizen science projects, especially the Personal Space Weather Station, because I personally believe that creating really high dimensional data sets, so having the imagery alongside, for example, magnetometer readings, will be the next step in really making NODAC a valuable scientific tool. So with that, thank you for your attention. And also, really quick, this shot actually was from Wednesday morning. And I took that up near Wiseman, Alaska. So that's 60 miles above the Arctic Circle, just for context. Yeah. Thanks.